Okay, mic podium, check, online. And then we have mic one, online. And then we have mic two, online. And then we should have mic three online on YouTube. Do I still see the captions? Okay, this is still the mic check for the GFN workshop. Do I have any captions on the screen?
Et maintenant?
Mic one.
At least the first 2 days, yes.
OK, un petit dernier mic check pour YouTube. Mic 2. Petit dernier mic check pour le micro 1 sur YouTube. Un petit dernier mic check pour le micro podium sur YouTube. Et un autre petit mic check pour le micro 3.
Vas-y, vas-y. Super, merci.
Mic 2, hello. Mic 1, bonjour. Podium. And mic 3. Podium, mic 1 and 2 and 3.
Je vais le mettre dans mes notes. It's on, it's on the website, and we're gonna put it on Zulip too. You're welcome. Hello. Je viens faire un refresher sur les probabilités. Demain, ça? En tout cas, après,
Just me for some stuff here and there.
he just told me.
That's like contact. Huh?
Yes, sorry.
Okay, wonderful. Anyway, yeah, I messaged Victoria. Oh,
Taking a while. Not trusting.
did you hear the story there?
Oh, I need to like hit like I and J for everything. I say wait, and I. like a different one. I don't, if I was just like that, hey, so. What I want to, yeah. Yeah.
Um,
Still don't know anything about my. And now, I'm gonna buy their. Yeah, now, and say.
ouais, demain.
Yeah. I really like your thing.
Hello. Okay. Morning, everyone. We're a bit late, but that should have been expected. We're gonna get started. So thank you for being here. I'm glad to see so many people on a cold Wednesday morning. I'm Victor Schmidt. I'm a final year, hopefully, a PhD student here at Mila with Yoshio Benjo, and I will chair this 3-day workshop. We've designed the workshop to be very gradual, focusing on the understanding of GFlowNet and why their motivation, why you need them, rather than exploring the frontiers of the ongoing research. As you may already know, GFlowNets are amortized variational inference algorithms that are trained to sample from unnormalized target distributions over compositional objects. All right, if none of that made sense to you, or only partially, that's fine. That's actually why we're here today, so don't worry. Tomorrow, we'll delve into the theory with opening words from Yoshua. Stuck with me today. And on Friday, we'll discuss practical applications and challenges with training GFlowNets. Each day will be chaired by a different researcher who has been in charge of designing that day's curriculum. So I want to thank them and the whole team in general for making this workshop happen. A few months ago, when I started to get more serious about GFlowNets, I saw two options: either read the papers or organize a workshop and have the authors explain them to me. So here we are. A few logistical details. Don't lose your badges. You'll need them tomorrow and the day after. We have set up a Zulip chat room. You've seen that. All right, that was up. So scan the QR code, and that chat room will be where we can post papers, references, where you can discuss and have questions online. Importantly, the first 2 days of this workshop will be streamed on YouTube. The link is on Zulip, on Mila social media, and it will stay there if you want to access the recording later on. If you need anything, feel free to reach out to any of us with this black t-shirt. We're the organizing team, and we'll try to help you. Not all talks will take questions, but for those who do take questions, if you have something to ask, please do use the mic in the alley, and there's another one over there, so that everyone can hear you, especially people online. Something that is not a logistical detail, though, is to understand and acknowledge the history of the land that we are on. And so I will read a paragraph to that effect. So we would like to begin by acknowledging that Mila is located on unceded indigenous lands. The Ganengehaga Nation is recognized as the custodians of the lands and waters on which we gather today. Jojage, or Montreal, is historically known as a gathering place for many First Nations. Today, it is home to a diverse population of Indigenous and other peoples. We respect the continued connections with the past, present, and future in our ongoing relationships with Indigenous and other peoples within the Montreal community. Mila acknowledges the systematic barriers that Indigenous peoples face with respect to education, employment, land, and technology. Indigenous knowledge and science have typically been devalued, excluded, and erased from AI science, and we therefore recognize the need for a commitment to work with Indigenous peoples in AI research and science. Now that we know where we are and where we're going, let me welcome the chair for our first day today, Tristan. Tristan Deleu is a final year PhD student working with Yoshua Bengio. He's one of the core contributors of GFlowNet and is leading the work on applying GFlowNet for causal discovery at Mila. You can stand back up.
All right, thank you. Yeah, perfect. Oh, okay. Yeah, thank you, Victor. So yeah, my name is Tristan. I'm going to chair part of the part of this first day, which is about introductory materials. So as Victor said, we wanted to make this workshop as accessible as possible for everyone, with various backgrounds. So we don't want to assume anything. So maybe the things that we're going to talk about today is going to be very basic for many of you, but this is really on purpose. So we're going to start gradually with the first presentation on really introduction to probability, and then going through probabilistic modeling, probabilistic inference. So these are maybe things that you've seen. And then in the afternoon, we're going to look at some of the things that are more related to what GFlowNets are actually used for. So essentially sampling, and also some connections with the reinforcement learning literature, which you might be familiar with, and you may know that GFlowNet it's taking some inspiration from reinforcement learning. Unfortunately, we won't have this last session, the practical session, due to technical reasons. So we will just stop at around 3:30 today. So that being said, I want to introduce our first speaker, who is Vittoria Barimpasela. So Vittoria is a PhD student with Simon Lacoste-Julien here at Mila and University of Montreal. She's also a visiting researcher at Meta, where she's working with Pascal Vincent, and she's broadly interested in the topic of causal representation learning. And she's going to talk about introducing us to the realm of probabilities. So please welcome Vittoria on stage.
Good morning. Thank you, Tristan, for your introduction. Yeah, so as Tristan mentioned, I will kind of give an introduction to probability, maybe directed towards someone from outside of the field, or maybe for some of you, it's going to be just like a simple review or recap of basic probability. So yeah, it's going to be kind of informal. Don't expect anything too rigorous, but hopefully it'll be helpful. So first, although this is, can you hear me well if I speak from, good. So the theme of this lecture is Introduction to Probability, but it's also a little bit about statistics. And I want to talk about the difference between probability and statistics, because that's what we're here for. Maybe machine learning is a little bit more like statistics. So in probability, you have a probabilistic model, and the question you're asking is, let's say like I'm tossing a die, and I want to know the probability of getting number 1. On the other hand, statistics is more like the inverse problem, where you have the data and you're trying to learn the probabilistic model or the parameters. So basically, you can have like a series of coin tosses, and from that you want to determine like if your die was biased or not, or what is the probability of getting each of the numbers. So here is the plan of what I'm going to present. I'm going to start with random variables, probability density functions, and probability mass functions. I'll give some examples of typical probability distributions. I'm going to present general probability concepts like conditional, marginal, sum rule, product rule, and the Bayes theorem. And then in the end, I'm going to drift a little more towards statistics and talk about maximum likelihood estimation and Bayesian learning. So let's start with random variables. Basically, a random variable can take different values from a set. And each of these values is associated to a probability. If you have discrete random variables, it means that your variable takes integer values. For example, if you're rolling if you're rolling a die, your x can take values between 1 and 6, but not like 1.5. And the probability of each of these values that it can take, if the die is unbiased, is going to be the same for all of them, 1/6. And here we call that the small x is the realization of x, of the random variable x. And this can be represented, for example, by a table where you have the probability for each value that it can take, or or by a plot like this, which is the plot of the probability mass function, or a PMF. So the PMF is the probability defined for discrete values. And well, this is not just like a general function, since it's a probability, it has a few properties. For example, the probabilities are always non-negative. So the probability is between 0 and 1 usually. And it cannot be minus 0.5. And the probability across all the possible values that it can take will sum up to 1. So this is basically basic definitions. But we can make this like slightly more complicated and talk about obtaining values within a subset of your domain. So let's say you don't want to get the probability of getting just 1, but the probability that the value of the die will be 2 or 4 or 6. And since this is an OR kind of operation, you're just summing these probabilities. So in this case, it will be like 3 times 1/6. And now we're talking about continuous random variables. So as opposed to discrete random variables, these continuous random variables can take any real value, really. And they will define a probability density function, or PDF. And we have an important difference here, which is that we're now looking at the area below the curve, and the curve is definition of. We're using this notation that P of X equals small x, which is like a single value. And in this case of a PDF, this probability would be 0, because in the PDF, we're not talking about intervals. The probability of X belonging to an interval, let's say between A and B. And one consequence of this new definition that we have now is that like one simple way that will replace the definition we had before is that we're going to replace the sums by integrations. So the properties are kind of the same. The probabilities of X belonging to an interval, given that this interval is in the domain of X, should be always greater than 0. And the area under the PDF should be 1. Now I'm going to give just like an example of a very popular kind of PDF, which is the normal distribution or the Gaussian. So for one variable, which is what we're talking about so far, the PDF of the Gaussian is going to be given by this expression over here. And it is represented in figure B. So basically, this is a standardized Gaussian, which means that it has mean 0 and variance 1. So you can see that most of the bias is at 0, and the variance of this Gaussian is 1. But you can also have more than one variable. So for example, in C, we have 2 Gaussians. So this axis is one Gaussian, and this other axis is another Gaussian. And it has basically the same shape, but in 2D. It's given by this expression. And you can kind of even like visually see that the area under the curve is, or in this case, it's the volume. And in A, we simply have like the samples that we would get from this 2D Gaussian in C. Basically, when you have like a probability distribution like this, you can also, if it's in closed form, if it's like a typical distribution like the Gaussian, you can sample from it easily, which means you can get those, we can get those samples and they're centered around 0 and they have like similar shape. But I believe there will be like a tutorial only on sampling later. And here's an example of a PMF. It's the Bernoulli distribution, which is the example I've been using to motivate this lecture since the beginning. It's basically a coin toss where theta is the probability of getting ahead, for example. And the observations you can get from your coin toss can be heads or tails. So you have 2 discrete values, 0 or 1. And the way this is typically written is like P of S given theta, and it's going to be equal to the probability of the data given the parameter. Or it can also be written in shorthand notation like this, which means basically that X is drawn from a Bernoulli distribution with parameter theta. And then in this case, the PMF is given by this expression. We can read it like slowly. So for example, P of X being 0, which is P of X being head, given theta being, let's say, 0.5. If we have an unbiased coin, is theta to 0 times 1 minus 0.5 to the power of 1 minus 0, which is 1. So this is like a simple expression that can account for both cases of X being 0 or 1. And here's a simple visualization of this PMF given different values of theta. Basically, like in dark red, you have theta being 0.2. In dark blue, you have theta being 0.8. In dark green, you have theta being 0.5. And basically, these two realizations are going to sum up to 1, or their probabilities will sum up to 1. I need my water bottle. And now you have, well, I just informally showed you like that you can have more than one random variable. And so we can define a random vector x, which is basically the concatenation of all the random variables from x1 to xd. And then the joint probability of all of these random variables is going to be written like this, like P of big X equals X, where X is all the realizations x1 to xd. It is an AND kind of operation now. It's a probability of getting x1 and x2 and up to xd. And it can also be written like this. So I'm going to show you later how it looks. But now let's talk about the marginal, because there is a difference between the joint probability and the marginal probability. Here, imagine a case where you have two variables, x1 and x2. The marginal of x1 is the probability of x1, which is basically the joint summed over all the values of x2. And here I'm writing this for with like discrete variable notation, but it's basically kind of the same idea for continuous variables. So here's the example. Here we have in A samples of the joint x1 and x2. So the joint is really like this function of two variables. And in B, basically it's a function of only one variable. Here it's the marginal over, I think, x2. So basically what we're doing is like we're folding A, and it has a shape like this, which we can see between minus 1.5 and minus 1, the probability will be 0. And then beyond that, it will always increase because you're increasing the amount of points here. This is the continuous case. So in general, we can write it like this. Well, it's the same thing, but just like for multiple variables, you have a sum. The marginal of x1 is basically a sum over the variables that all the values that all the other variables can take. And then in the continuous case, it's the same thing, but you have integrals instead. And notice that this is going to be very computationally expensive in a high dimensional case, because you have to compute all these integrals. And now let's talk about conditional probability. Conditional probability is the probability of, for example, x1 given x2. And it's given by this expression. It's the joint of x1 and x2 divided by the marginal of x2 that I just defined. So we can go through this in detail. Here I have all the realizations of x1 and x2 in the discrete case. And here I put explicitly the marginal of x2 being the sum of the joint over x1, over all the values that x1 can take. But I'm going to show you actually how does it look like in the continuous case. Here's the same joint, the same samples of the joint as we had before. And the conditional here is like slicing, basically. Or like you're fixing the value of one of the variables and you're looking at the distribution of the other variable. So basically in C, you have the conditional of x2 given x1 equals 0. So if you look here in A, we'll go to x1 equals 0, and we slice it over here, and we look at this segment and the distribution of x2 on this segment. We can see it looks like pretty homogeneous, like uniform. So between minus 1.5 and minus 1, there's like 0 probability. And then between minus 1 and plus 1, we have this uniform probability, which seems to be 0.5. And beyond that, it's 0 again. Then again, for in D, we have the same thing, but a different slice, just to be very clear. Here, we have the condition of x1 given x2 being 0.75. So it's basically slicing it here. It's this small segment. And we're looking at x1. It's 0 for x1 less than minus 0.45 and greater than 0.45. And otherwise, it's like uniform in this inside this area, this segment. So here's the general case for multiple variables. Basically, you have the probability of one variable given all the others. It's equal to the probability of all the variables divided by the probability of all the others. And here, basically, the probability of all the others is this marginalization over the variable x1 that you're considering. Okay. So you can use the conditional probability in the Bayes rule, which is basically a way to invert the conditional. Let's say you have you want to know x1 given x2, but you have access to only x2 given x1. You want to get one as a function of the other. So from the definition of conditional before, I think, by the way, people may not always present the Bayes theorem like this, but this is how I always remember it. Like, I need to rederive it, otherwise I'll mess it up. So let's go and define the conditional of x1 given x2 and x2 given x1. So here is just the definition I put before. But now for one of them, we can rewrite it like this. Basically, I just put the p of x1 to the left side. And now we have the probability of the joint, p of x1 and x2. And we can replace this right here in the previous definition of x1 given x2. So here's the same definition, but now with this instead. And that's it. Now we have the probability of x1 given x2 as a function of probability of x2 given x1 over the marginal of x2. This is the Bayes rule. Now, one example, or like maybe like a more clear way to write this in the discrete case again, would be, let's say like you're doing classification and maybe x1 is a class, cat or a dog, and x2 is a feature. It could be the nose size, it could be the nose length, for example, some measurement you have. And now you want to know the probability of your thing being a dog given the length, this feature, and you have it as the probability of x2 being the length given the class dog, and the probability of having dogs in your data. And then here in the denominator, I rewrote the marginal as kind of a conditional. So basically, this is the probability of x2 given x1 times the probability of x1 summed over all the values of x1, which is all the classes, so cats or dogs. So this is how it's kind of used in naive Bayes, for example. And well, this is the general definition of the Bayes theorem. for multiple variables, you can always write p of x1 given all the other variables as a function of all the other variables given x1. And in the continuous case, the denominator will be an integral. Okay, so going back to the conditional probability, we can apply it successively to the joint. So you have the probability of x1, x2 up to xd, and then you can write it as the probability of x2 up to xd times the probability of x1. And then you can do it again. For this probability of x2 up to xd will now be the probability of x3 up to xd times x2, and then you had the probability of x1 from before. And you can apply this recursively and basically obtain this factorization, which can be useful, just mentioning it. Yeah, and now independence is a property of the random variables. Basically, if x1 and x2 are statistically independent, it means that any information you can have on x2, x1 will not inform you about the value of x2 and vice versa. One way to write this is that the probability of x1 given x2 equals the probability of x1 and the other way around. But in general, let's say you can say that x1 up to xd are mutually independent. That is, x1 is independent of x2, x3, up to xd, and all the variables. Then you can write it like this. Then the joint factorizes as the product of the marginals. And this is very useful, and we're going to use it later. Okay, now I'm going to talk about maximum likelihood estimation, which is switching a bit more towards statistics. So a statistical model describes the PDF or PMF of your observed random samples or random variables using parameters. And the setup is that you have access to your observations. You have like n of them, and your sample set has size n. And these observations are independent and identically distributed. It means that, let's say in the coin toss example, every time you toss a coin, well, you're tossing them independently, right? Each result you're gonna get, head or tail, is independent of the other. And then, since you're tossing always the same coin at the same time, and it has the same probability of getting heads or tail, your distribution is also, your samples are always coming from this identical distribution. It's always the same, because your parameter is the same. And the goal for MLE is, given all these observations, you want to estimate the parameters, or theta in this case. So we can write the likelihood that the data was generated by the parameters of your model. We'll go through this slowly. First, the probability of the data is the probability of the joint x1 up to xn of your observations, but it's conditioned on the parameters. And since each of these observations are independent of each other, we can use the independence property that we just showed before to factorize this into the product of the conditionals of each xi given theta. And this is called the likelihood. And then in maximum likelihood estimation, we want to maximize the likelihood that the data was generated by the parameters. So basically, you're maximizing this over theta, which is the parameter you want to estimate. And the maximum value would be your estimation. However, in machine learning and computational statistics, usually logarithms or probabilities are like more computationally stable and more useful. So we can instead take the log likelihood, which is the log of the likelihood. And like here in the second line, remember that the log of the joint probabilities is the sum of the logs. So the log likelihood can be expressed by this. And since the logarithmic function is monotonically increasing, if you maximize the log of the function, you'll be maximizing the function. So then basically your estimated theta will be the argmax of the log likelihood over theta. Okay, and here's the Bayesian approach to like the MLE, which I just presented, is basically the frequentist approach to parameter estimation. And the Bayesian approach is a bit different because it treats the uncertainty as random variable. So whenever you have uncertainty, you kind of like put a belief on it, which means you put a prior on it, and then you apply the Bayes theorem. So here's how it's defined. This is basically the Bayes theorem, but for your variables are now the parameters in the observations. So you have the probability of the parameters given your data being the probability of the data given your parameters, probability of the parameters, which is the prior, divided by the marginal, P of X. Here, P of theta given X is called the posterior belief. And it is usually what is kind of either maximized or what you want to get, because intuitively it makes sense if you want to like optimize directly for theta and not for X given theta and then maximizing over theta. Here, P of X given theta, this term here is the likelihood, basically like we had before. So it's the observation model. And P of theta is the prior belief, which can be conditioned on hyper priors. Let's say if you have like some kind of belief on various degrees of uncertainty, you can keep growing this with more priors. And then P of X is the normalization or marginal likelihood. So I would basically mention like two ways of doing this. One is the Bayesian way. One is the posterior means, which means that your estimate is the expectation of your posterior, basically like your expectation of theta given X. And the other approach that I personally consider the Bayesian approach, maybe it's not pure Bayesian, but it's maximum a posteriori or MAP. And basically here, it's like I said, you're optimizing. Basically, here's the log of the posterior kind of, and you're maximizing this over theta. And well, I thought I wouldn't have more time. I see there's still a few minutes, but I can stop right here. And if you have any questions, I also wanted to mention that these slides have been inspired. I forgot to mention before. It was nicely inspired by lecture notes by Simon, Pascal, and Apple. So a lot of the pictures you have here have been taken from them. And that's it. Thank you. I hope it's kind of helpful. Yeah, beste. Oh, sorry, I forgot.
thanks, Victoria.
Yeah. So here I had mentioned there's like, you can have a hyper prior, which is a prior on your prior. So basically you can have theta given alpha. And so you can have like, but I think in the case of like coin tosses, they put like beta distributions, gamma, and then like prior of gamma over beta, and so on. And you can put a lot of priors. Yes?
I didn't get what the difference is between your prior and hyper prior.
Yeah, sorry. I think I should have given like a complete example of this, but I thought it would run out of time. But a hyper prior is a prior you put on your prior. So let's say if your probability of here, let's say probability of theta has to be between 0 and 1, right? But you can put a prior on oh my god, how can we you can put a prior on this prior. Like let's say you have now the joint of P of theta being well, but maybe this is not the best example. Okay, can you help me with?
So yeah, so prior, you can think about it as being a priori knowledge that you have about the system that you want to model. So you can specify it if you have expert knowledge, for example, you can specify the prior. But what if you don't really know how to specify this prior knowledge in the first place? So you could say, okay, I don't know, I have some uncertainty still about this prior itself, so I can put a hyper prior on top of it to say, okay, I'm making even fewer assumptions about the system that I'm making. So as you go up, you're making fewer and fewer assumptions. Is there any other questions for Victoria? All right, let's thank Victoria again. And so now we have a little break, and so we have some coffee and pastries there, and we'll start again at 11.
Hello, everyone. Let's come back from the break and listen to another tutorial. Please take your seat. Okay, great, thank you. Okay, so the next talk is going to be by Tristan Dedeaux. He's the final year PhD student with Joshua, and he's going to talk about probabilistic modeling. The floor is yours.
Thanks, Sasha. So hi, everyone. It's me again. I'm going to talk about probabilistic modeling. So it will be a follow-up we're going to follow up from Vittoria's presentation, going from what are probabilities, what were conditional probabilities, Bayes rule, and everything like that, and how do we use these things? Like what is this actually used for in practice? Okay, so maybe one of the first questions that you may ask is, why do we want to use probabilistic models? Because like nowadays we see so many great applications of machine learning and AI, and we have so many powerful models that are doing great predictions all the way. And so you may ask, like, why do we want to put probabilities on top of it? Why do we want to do any of that? So I'm trying to give you a few reasons why this might be helpful to think about probabilities, in particular when it comes to modeling with machine learning. And so the main thing is that when you get a powerful predictive model, so let's think about like a powerful, nowadays like transformer, let's say, there is so a predictive model, they're not really designed to represent the uncertainty that you have about the predictions that they're making. So they're just making predictions, they're just making decisions, but they don't tell you how confident they are. And so this can be very risky because sometimes these models, they can make very wrong predictions with very high confidence. They might be very sure about like something that is going to happen, but without telling you, okay, I'm not really sure if the outcome is going to be what I'm predicting. So one of the examples of these risky situations might be in self-driving cars, and we see still within the past few weeks some news about it, where you may not want your car to just make decisions without really thinking about it. You want to also your model to be to give you some kind of knowledge about how uncertain it is about the situation that it's facing currently. And so these models, these prediction models, they can also be prone to be fooled by adversarial examples. So you might have seen some of these examples where you have some image that you can you see that is visually very close to, let's say, something that looks like a car, but actually is just adding a little bit of noise to the image that you're trying to predict, in order for the model to actually make the wrong predictions. And so it's not going to be a car, but it's actually going to be like just free road. And so maybe your car is just going to detect that there's nothing in front of it and crash into the car in front of it. So these predictions, it may lead to harmful predictions, harmful just like on the standard things, standard meaning of the word, but also from a fairness perspective, because maybe some of these models are going to make wrong predictions about parts of the population which may not be well represented into these data sets. And so if we had models that could also tell us how uncertain we are about the predictions that we're making, maybe these kinds of situations may appear less often. And finally, these very powerful predictive models, they are often lacking interpretability. And so one of the nice things about these probabilistic models, like some of them that I'm going to talk about today, it's that they are really good for making interpretable predictions. And so this, you may think that we don't really care about interpretability. At the end of the day, we just want to make good predictions. But in some applications, this might be exactly what you're looking for. And so, for example, when it comes to scientific discovery, what matters is not really what is the prediction that you're making down the line. It's trying to get an understanding about the world that you're trying to model. So all of these things, I'm not saying that probabilistic models gives you all of that for free, but this is kind of the direction in which we want to go when we talk about probabilistic models. So I want to go back to one of the examples that Vittoria talked about earlier, which is really the simplest kind of probabilistic model that you can think of, which is this model of, which is modeling tossing a biased coin. So let's say you want to model the outcome of flipping a coin, and this coin might be biased. So it's not the regular coin that you would have where you have 50-50 chance of eating heads or tails. This coin might give you more often heads than tails. And so the way you can model this thing is to say, okay, I have a probability of having my coin landing on heads, which has probability P. And then I have a probability of the coin landing on tails, which has probability 1 minus P, because we saw earlier that these probabilities, they have to be normalized. So the sum of the probabilities over the different outcomes here, there's just 2 outcomes. It has to sum to 1. So that's why we have P and 1 minus P. And so as Vittoria presented earlier, this model is what we call a Bernoulli distribution. So it's a Bernoulli model, and we write it with some parameters P, and we write it in this way. So we have X with this squiggly line with Bernoulli P, and this just means that the outcome X, so this random variable X that we have, is distributed according to the Bernoulli distribution. And so what can we do with this model? Well, so far, I haven't seen anything, and we've seen earlier like what we can do with this. But as a general rule of thumb, when you have a probabilistic model, you can generate some data. You can sample from it. So this is sometimes what we call generative models. So you may have heard this whole revolution of generative AI. This is really one of the simplest examples of what you would have as a generative model. And you can generate data. So if you have, let's say, your random variable, which is distributed according to a Bernoulli with 0.5 probability of landing on heads or tails, then you can generate data. So you can simulate this flipping of coins as much as you want to get as much data as you want. And we'll see later why we would like to do this thing, and throughout this workshop, why this would be a good thing to be able to sample things from a probabilistic model. So this Bernoulli model, we saw that it has some parameters P, but what if we don't know what's the parameter P? And so we saw earlier that this is these 2 directions between having a probabilistic model and doing statistics. So here, if we have access to a data set of observations, we may want to find what are the parameters that could explain this data set that we are observing. And so this is what is all about statistics. So let's say we have a data set of 10 observations, 4 of them are heads and 6 of them are tails. And one way that we saw how to find the parameters that could explain these observations is through maximum likelihood estimation. So maximum likelihood estimation, Vittoria presented the general way of thinking about MLE, but really the underlying principle is that what is the parameter that best explains the observations that we're seeing. So this is very intuitive when we see this very simple model here. The parameter is just the number of times we have heads in our data set over the size of the overall size of the data set that we have. So here it would be 4/10. So we saw that this coin was slightly biased because we saw that it was not quite 0.5, it was 0.4 the probability of landing on heads. But now what would happen if we see a situation where all of the observations that we're seeing are just tails? So does that mean that we are never going to see heads? Because if we were to use the maximum likelihood principle that we saw earlier, it would mean that the parameter that best explains this data is actually 0. So we have 0 probability of seeing heads, which is, well, it's fairly unnatural. Maybe we were just unlucky in the data that we were seeing, even though it was identically distributed. But this is the kind of situation that could happen. And so another way of seeing that is to take a Bayesian perspective. So instead of really trying to find what's the single parameter that can best explain the data that we're observing, we could say, okay, I have some prior knowledge about the world. So we could say maybe there is an equal probability that my parameter is going to be either 0, 0.1, 0.2, up to 1. So this could be a uniform distribution over all the possible values that these parameters P could take. So this is the graph that we see on the top. And then the Bayesian perspective tells us how to change this belief that we have about the world. So we start with having no prior knowledge whatsoever. We have equal chance of having all the models that could explain the data. And then once we observe some data, we update this belief. So we go to this posterior distribution. And this is just another distribution that will tell us how likely we are to that these parameters are actually explaining the data if we observe this amount of data. So this changes from what we saw earlier, because if we observe no heads and 10 tails, then the distribution that we will get for the posterior distribution is, of course, going to be concentrated around 0. It's not going to be just 0. We have still some chance to have the probability P to be very, very small. And so we still leave the chance for the model to model these kinds of situations where maybe we were just unlucky in the data that we're seeing. And this is very important, especially if the amount of data that you're seeing is very small, because maybe you don't see all of the possible outcomes that could happen in your for your random variable. So here we're really taking that into account from the Bayesian perspective. But we're not really losing anything when we're looking at the Bayesian perspective, because if we take the example that we saw earlier, if we have 4 heads and 6 tails, we saw that the maximum likelihood estimate was 0.4. And then if we're taking this Bayesian perspective, we see that the posterior distribution is going to be somewhat concentrated around 0.4, but it still leaves the chance for some other values of the parameters to also exist. So this is really related to this concept of regularization in machine learning, if you're more familiar with that. And the maximum likelihood estimate tends to somewhat overfit to the data that you're seeing. So here we're leaving the chance of different other models to also exist. So I'm going to go quickly over that because Vittoria also talked about this, but we have some very basic probabilistic models that exist that can model different kinds of data. So I'm just highlighting some of the very basic building blocks that we can play with. So we saw the normal distribution earlier. We can also have some uniform distribution over continuous variables. The Bernoulli model, which is the one for the coin toss that we saw earlier. We can generalize that to cases where we have multiple outcomes, multiple values that the random variable can take, which is a categorical distribution. And then you have also this Poisson distribution, which is what you would use, for example, if you want to model some counts. So in some biological applications, you have some counts of things that you are going to observe. And so this is the natural distribution that you can use for that. So these are really, you can think about them as being building blocks, and we can use them, combine them together in order to build something which is a little bit more complex. And so how do we do it? How do we have something which is, how can we model something which is going to be more complex? So if we have a complex system, what we want is not just to model the distribution over a single variable, but we want to model a whole joint distribution. So we saw earlier what is a joint distribution. This is the probability of x1 and x2 and x3 and so on. And so we have different parts that we want to define the distribution over. So here I have an example where I want to define a distribution over, for example, the season, whether we have the flu or not, whether we have hay fever or not, whether we have muscle pain, and whether we have congestion. And so we have some natural connections between these different random variables, which I showed here. And we can leverage these natural connections in order to build our probabilistic model. And so one of the reasons why we may want to do that is because it might be very challenging to define a joint distribution in general. Because if you think about it, this joint distribution between x1 to xd, I need to define what's the value of the probability for each possible outcomes that all of these variables jointly can take. And so if you have, let's say, x1 that can take two values, x2 that can take two values, and so on, all of these variables are binary. What you end up with is having to specify an exponential number of different values because you have all of the possible outcomes all of these different variables can take. So this is very expensive because like your system, you can have many different parts that is making your system. You can have multiple, each of these pieces can take multiple values. So it's really going to be very expensive very quickly. So one of these ideas, which is behind something which is called Bayesian networks, and this is one of the illustrations that we have here, is instead of defining the probability of each of these possible outcomes individually, we can modularize the joint probability distribution in such a way that each piece can be modeled as a probabilistic model. And then we just have to specify the model for each of this individual piece, and then we combine them together in order to get an overall probabilistic model which is powerful for the whole system. So in this example, instead of having the joint distribution between all of these different variables, we can say we can decompose that into the probability of the season times the probability of flu given the season, and so on and so forth. So maybe it's very easy to specify what's a probability distribution of having the flu given the season, because it's more likely to have the flu during winter, for example, than it is during the summer. And the opposite for hay fever. It's more likely to have hay fever during spring and summer than it is during the other seasons. So each of these pieces might be easy to model, and then we combine all of them together to get something which is more complex. So what can you do with a probabilistic model? So I told you, I motivated why you may want to get a probabilistic model compared to your standard prediction model that people have been developing in machine learning. But why would you want to have a probabilistic model? Concretely, what do you want to do with that? So we saw earlier that we can use that for sampling or for generating data. So if you have this probabilistic model, we can just sample some data to look like some fake outcomes of this probabilistic model. We saw also that we can learn the parameters from data. So if we're given a data set of observations, how can we find the parameters for this probabilistic model? We can also use it, and this is where it becomes very interesting. We can also use it to answer questions. So we can answer questions, for example, what is the probability that I will be late at work? I will be late for work given that it is raining. So this sounds a lot like what you would have, write down as a conditional distribution that we saw with Vittoria. And so this is precisely why having a probabilistic model might be helpful. Like this is the kind of questions that we can answer with that. And this is a whole field of what we call probabilistic inference. So if you hear probabilistic inference, it means answering questions. And so we'll have a session right after presented by Sébastien, where we will see how to use these probabilistic models in order to answer these kinds of questions. And then finally, we're not losing anything. We can still do predictions with these probabilistic models. We're just adding some new features on top of it, and still get these predictions capabilities of these models. All right, so I want to talk about like a very simple example of a probabilistic model, which is very crucial in the whole literature on probabilistic models, and we'll also use that in the coming days, some of these notions to when it comes to GFlowNets. So, and this model is called the Markov chain. So let's say you want to model a sequence of objects. So when it comes to sequences, usually what people use is just language models. But I'm taking another example, which is actually RNA sequences instead. So RNA sequences, you have just a sequence of characters, and each of these characters can take one of 4 different values. So either A, C, G, or U. And if we want to specify a distribution, like a probability distribution over sequences, we need to specify a joint distribution over all of the joint distribution over all the characters that are making this sequence. And so we saw in the presentation earlier that this joint distribution, as a general fact, we can use the chain rule to decompose that as P of x1 times P of x2 given x1, and adding to the conditioning along the way to end up with something which is P of xt given everything else that we've seen in the past. And so if we think about how many parameters, how many values of the probabilities we need to specify for this model, where we're still in the same problem as we saw earlier. Like since this decomposition is very general, we still have to specify an exponential number of values for the probabilities of each possible outcomes for this general model. So this model is what we call an autoregressive model, because we're generating things one at a time. And so we still need to specify this conditional distribution over xt given everything that came before, and this has to be specified for all the possible choices of the past. So we have to take into account all of the history before we are trying to predict what's the final character of our sequence. So this will be expensive, and so an alternative way of modeling this kind of problems is to model that as a Markov chain. So instead of specifying all of these very complex conditional distributions that are growing over time, and we have to specify a lot of different probabilities for each of them, what we're going to do is make the assumption that if we want to, what the predictions that we want to make, the probability of the next character does not depend on the whole history before it, but it only depends on what we see currently. So what it means in terms of the joint distribution, it means that when we want to model P of x1 to xt, the joint distribution, this is P of x1 times P of x2 given x1 times P of x3 given only x2, and so on. So each of the conditioning only depends on the previous character. So of course, we're making a strong assumption here. We're saying that each character only depends on the previous one. So we're losing a little bit in terms of expressivity. And it makes sense because in terms of the number of parameters that we have for this model, we'll have much fewer parameters when it comes to a Markov chain compared to the general case with an autoregressive model. But it's still very convenient in many applications to look at these Markov chains. And it's especially, we'll see that it plays an important role when it comes to GFlowNet tomorrow and the day after. Another class of models that I want to highlight, which might be also very interesting in many applications, is the class of model which are energy-based models. So what we saw so far is that each of these, all of these probabilistic models that we saw, they have to be normalized. So we need to use building blocks that are made of distributions that are properly normalized. And so maybe this is very limiting because if we are modeling something which is very complex, like let's say how to generate an image, for example, when it comes to the generative AI, if we want to specify what's the distribution for over the space of images, well, it doesn't really look like the Bernoulli distribution that we saw earlier, or even the normal distribution that we saw. So it's much more complex than that. And so another way to specify, to have more flexibility in our definition of a probabilistic model is to define it using an energy function. So we're going to specify the probabilistic model only up to a normalization constant Z, and we'll just specify this energy. And this energy, you can think about it as measuring how compatible different things are together. So I'm showing a few examples on the right-hand side. So let's say we have an object recognition application, but we don't necessarily know how to model exactly going from the image to the probability over the labels of this image naturally. But what you can do is to feed all of these in these two components into an energy function that tells us how compatible these two objects are going to be together. So let's say, for example, if we have an image of a cat and the label cat together, then they're going to be more likely to go together compared to if it was with an image of a dog. So with the label of a dog, sorry. So this is really a very flexible way of specifying probabilistic models. But the challenge here now is that we still have this normalization constant, this Z, which corresponds to summing over all the possible outcomes that we have for the variable, the random variable X can take. And this thing can be very, very hard to compute. Like in general, you cannot enumerate all the possible outcomes that X can take for the same reasons that what we saw earlier. Like there might be an exponential number of these outcomes. So this normalization constant is in general intractable, and this might be this makes things very difficult to do. So like some of these features that I presented earlier when it comes to having a probabilistic model, so just sampling, learning from data and stuff like that, becomes more challenging when it comes to an energy-based model because we don't have an explicit access to this normalization constant Z. So this is where things can get a little bit tricky, but luckily we'll see some applications of GFlowNet where we can actually use GFlowNet to answer some of these, to address some of these challenges. And so I want to go back to like as an application, not direct application of energy-based models, but taking inspiration from what we just saw. So if you remember when we talked about the Bayesian perspective, when we talked about posteriors, that posterior distributions that were encoding some belief that we have about the model which is describing the system. This is also defined as a probability distribution up to a normalization constant. It's really the same thing. We have P of D given P, which is the likelihood, if you remember from Victoria's presentation, times P of P, which is the prior, and then we divide by something which is the normalization constant. And the same way that we saw that in energy-based models, this constant Z was very challenging to compute, and it's intractable to compute in general. When it comes to Bayesian posteriors, this evidence, this P of D, the normalization constant, is also going to be intractable in many cases. And so we still are in the same situation as what we saw for energy-based models. And so GFlowNet's, what the whole purpose of this whole workshop, what we'll see in the coming days, is that GFlowNets, there are going to be a class of probabilistic models where you can specify the model up to a normalization constant, and you can still use, you can still answer all of these questions that we saw earlier. So learning from data, sampling using the GFlowNets, but we'll see that at least tomorrow. And I just want to finish the presentation just to say that, okay, I gave you a very basic introduction to probabilistic models, but it's not just about like these very, very basic models. Nowadays, we have probabilistic models that are doing amazing things that can generate really high dimensional, very structured, very complex data. And so this is something that we still need to acknowledge. So, for example, we have GANs that were all the craze these past few years up until, let's say, 2020. And then more recently, we have also this class of models called diffusion models. And so these two things, if you've heard of these models, and probably diffusion models lately, which have become more powerful, these are also examples of probabilistic models, because we're generating some data, we're sampling data, and so we can still interpret them as probabilistic models. And so this is just to say that there are some really real world applications of these probabilistic models, not just the coin toss that I explained at the beginning. All right, so that's it. I want to thank you for attending. I'm just showing a few good resources if you want to go a little bit further when it comes to probabilistic modeling. In particular, the probabilistic machine learning book, which is very good, very recent resource, which is covering a lot of these very well-known, well-established probabilistic models, but also these new probabilistic models that I briefly touched upon lately. And then some of these other books, which are more better, also good references when it comes to classical probabilistic machine learning. That's it. Thank you.
Maybe we have time for a couple of questions. Do we have any questions in the audience? Yes, could you go to the mic, please?
When determining like the result of an energy-based model, how exactly, as you said, it's a level of similarity, I guess, that you go and get. Is it from 0 to 1, or is it an energy base? It could be anything.
Exactly. So the energy can be really anything. So that's really the beauty of specifying your distribution up to a normalization constant, is that these values of the energy can be really anything, and then you will get a probability distribution by normalizing it down the line. So the only constraint that you have when it comes to probabilities is that they have to be positive as well. So we need to make sure that these probabilities will be positive, but this is guaranteed by taking the exponential of your energy. So but the energy itself can be really anything, and in various applications we have the energy can be really positive, negative, anything like that.
So that would lead me to my next question, which is, in that case, when you're building a data set for that, how do you determine arbitrarily the energy of two different elements?
So there are different ways of specifying the energy. Maybe you have some physical like physical model that can give you what's the energy of a particular example. So for example, I'm not an expert, but I think when it comes to drug discovery, we can have some binding energy, for example, that we have some models that can give that to us. And so we can use directly this oracle for the energy to directly get the energy. And then you have the other approach, which is that we can also learn the energy. So the same way that we saw earlier that we could have a probabilistic model where we know the parameters and then we can use them, we can also go the other way around, the statistics way, where we have the probabilistic model, we have a data set, and then we can learn the parameters of this probabilistic model, which here would mean learning the parameters of the energy function. And so you have plenty of methods of learning this energy function. You can use gradient-based methods. So this was really popular. I want to say like in the mid-2000s when with some things like Boltzmann machines. So the predecessor of this deep learning craze. So these, if you've heard of Boltzmann machines, this was really an energy-based model down the line. So you can still use gradient methods to train these things from data.
Thank you very much.
Thank you.
Okay, let's thank Tristan again. And yeah, I'll let Tristan introduce our next speaker.
Thank you. So our next speaker is Sébastien Lachapelle. Sébastien is a research scientist at the Samsung SAIL lab. He's working broadly on causal representation learning. And today he's going to talk about, he's also a PhD student at Mila. And today he's going to talk about probabilistic inference. So please welcome Sébastien.
Right, thank you. Hello, everyone. My name is Sébastien Lachapelle. Yeah, I'm a PhD student here at Mila and also a research scientist at Samsung just over here. So today I've been asked to talk about probabilistic inference. So that's what I'm gonna do. Let me just set a timer. There we go. Yeah. Yeah, so we're going to see what is probabilistic inference together. I'm going to give some examples of tractable inference problems. So we're going to see the Markov chain, an example that Tristan covered before. We're going to see the Gaussian mixture and also factor analysis. Then we're going to try to make these examples a little bit more interesting. But by doing that, we're going to make the inference problem intractable. So we're going to see that. And then we're going to see like two broad categories of approaches to deal with these so-called intractable inference problems. So we're going to see sampling-based inference. So today, so in this lecture, I'm just going to give like a high-level view of what that is. I think that's the topic for the next lecture. And then I'm going to talk about variational inference. And I will sort of build up towards variational autoencoders, which some of you might know, but maybe not from that exact perspective. So let me jump in. So what is probabilistic inference? So probabilistic inference is simply the computational problem of computing different queries about a given probabilistic model. Okay, so you might, let me just find my laser pointer. There you go. So you might have your probabilistic model for n random variables. And, you know, probabilistic inference is simply the problem of computing various quantities like marginal distributions or conditional distributions. And, you know, we already saw these objects in the previous lectures. So let me just explain this notation quickly. So I'm going to say that XS here is essentially the subvector of X made of the coordinates in the subset. So S is a subset of indices, and XS is essentially a subvector of S corresponding to these indices. And so that's the high-level idea. You might also want to compute various statistics about these objects, like expectation, maximum, argmax, all these things. And so we're going to see how we can tackle this. And of course, yeah, that's the distinction between discrete and continuous. And yeah, in the sum here, we have to sum over all the possible values that the vector XS complement can take. So here SC stands for S complement. So that's the idea. So we're gonna take an example. So this is the discrete Markov chain. So we have a chain of D random variables. These are discrete variables, and they can take k different values. And we're going to make the assumption that this distribution factorizes like this. So, so yeah, exactly. So essentially, you have the product of p of x times p of x given x1, and so on and so forth, up until p of xd given xd minus 1. And the probabilistic query that we're going to look into now is how to compute a marginal distribution over xd, so the last variable in the sequence. And so just using the definition of a marginal, what we're doing is simply summing over all the other variables, so integrating over all the other variables. So what we have to do here is we have to sum over all the possible values of all the variables except d, essentially. We can rewrite this sum as such. So you have multiple sums like this. And to go from this line to this line, what I'm doing is essentially just pulling some terms out of these sums. Okay. So for instance, here the term px1, it doesn't depend on xd minus 1 here. So I can sort of pull it out of the sum. Okay, and I can do that all the way up to the very last sum, right? Because x1 depends only on x1, so I can put it out of all of these sums. Okay, so it's sort of like a constant as a function of x2 and the later variables. And what I'm doing here is I'm just doing the same thing for every term. So I can also pull p of x2 given x1 out of all of these sums, and I bring it essentially here. So I'm doing that sort of recursively, and I get this expression. Of course, these two expressions are equal, but interestingly, they have different computation costs. So if you were to evaluate this sum naively, you would have to sum an exponential number of terms, so exponential in the length of the sequence, right? Because you can count the number of terms that you have in the sum, and essentially, yeah, you have to sum over all the possibilities, over all the possible values of x1, x2 up to xd minus 1. So it's an exponential number of terms. So that's pretty costly. Whereas if you try to compute this sum, you're going to have a linear cost in the length of the sequence. So essentially, what happens here is that here I'm summing over only xd minus 1. So I have k terms in this sum. Then you can evaluate this sum. You also have a cost of k, and you do that sort of recursively like this. And so you have to take d sums of k terms. So you have a cost of kd. So essentially, the moral of the story here is that even though these things are sort of easy to define mathematically, they like exactly how you're going to compute those things will have like a significant impact on the cost of doing that. And so yeah, that's the idea. And this is, by the way, a special case of a more general algorithm called variable elimination. And yeah, there is like a whole field of about that. Essentially, variable elimination works for general factorization. So here I'm just talking about the chain, but you can have more complex graphical models, as Tristan explained before. Any questions on this? Or I should take the questions at the end, maybe, or yeah, questions? All right. Okay, so yet another example of exact inference would be doing inference in a Gaussian mixture. So what is a Gaussian mixture? So you have a categorical variable z, which you don't observe. And for each category, you have a Gaussian density. So essentially, the density of X given category Z is a Gaussian with a mean and a covariance. Okay, and of course, the mean and covariance can change for different clusters. And so when you look at the density over X, that gives you this sort of bumpy density function. I'm not going to discuss how to fit this distribution to data. I'm just going to assume that you have this model and that you want to do inference. So here it's a very, very simple model. So inference happens to be easy, right? So we are in the tractable or exact inference section. So what we want to do is you are given a new data point x0, and you would like to compute the probability that this sample x0 belongs to the different categories z. Okay, so essentially you want to compute p of z given x0. So in that case, you can just apply. I guess this is the definition of the conditional. So you have the joint here in the numerator. You have the marginal in the denominator. You can sort of rewrite this in this way, and you get this expression. And it turns out that all of these terms you can, they are given by this model. So you can actually just go ahead and compute this sum, and that will give you the distribution of z given x0. Okay, so this is a very simple example where doing inference on a non-observed variable z is cheap or easy to perform. Does that make sense? Still, yeah. Okay. Okay, so I have a last example of tractable inference. So now we're gonna consider a latent variable z that is. So by the way, when I say latent, I mean hidden in the sense that you don't observe it. So now my latent variable will be a continuous vector instead of a categorical variable. We're going to assume that it's a normal distribution that is normally distributed with mean 0 and covariance identity. And now P of x given z is a normal distribution, but the mean is essentially a linear transformation of the latent vector z. And the covariance is just the diagonal, okay? Okay, so you might want to learn a model like this, maybe to learn an interesting representation about your data. So again, I'm not going to talk about how to exactly fit this model to your data. You could use the EM algorithm to do it. But so again, now I'm just going to discuss how to actually compute the posterior of z given x0. So again, it's the same story as before. We have a data point x0, and we want to compute, to have a sense of like what is the latent variable z that has given rise to this sample x0. So we want the posterior p of z given x0. And we're not going to look into the computations of how to compute that, but it turns out that you can compute this exactly. So there's a closed form solution to this problem, and essentially it turns out that p of z given x0 is still Gaussian, and the parameters of this Gaussian are given by some function of the parameters w and the covariances in the diagonal covariance here. So this is again an example of a tractable inference problem. I'm not giving you the details, but just to show you that in some cases inference is easy. You can just compute it. And of course, if you want to have the details about what is exactly the parameters of this posterior, you can look at Kevin Murphy's book. So, okay, questions about these simple examples? No, crystal clear, good. Okay, so all of the examples that I gave are tractable. You can compute the query that you are interested in exactly and cheaply. So now what I'm going to do is I'm going to make the examples that we looked at a little bit more interesting. We want to have like more expressive models. But by doing that, what usually happens is that inference becomes intractable or much more computationally challenging. So if we take the Markov chain example and we sort of relax this chain assumption and we just allow the distribution to be essentially any distribution, you get this this factorization, which applies to any distribution. In that case, if you try to apply, the trick that we saw of like pulling terms out of the sums to get a linear cost, you won't be able to do it because it's a general distribution. You will always be stuck with this exponential cost in terms of the number of variables. Okay, so this is an example where exact inference is possible, but it's just very costly for very long sequences if you consider a model like that. Another example would be to relax the factor analysis model that we saw before. Not relax, but like make the model more expressive. Okay, we'll go from a simple linear model to a deep generative model. Okay, so we're going to replace the linear function that we had here by a neural network parameterized by some parameter theta. Okay, so it's like the same model, but this mapping here can be much more general. Of course, this is a much more expressive model. You can express much more interesting distribution with a model like this. But again, there's an issue of like how do you compute these the posterior? Okay, so before we had an exact form for the solution. Now we're stuck with this integral essentially here that appears in the denominator, which is intractable. Because if you were like to open up this integral and write it down explicitly, you would have like this nonlinear function here appearing, and it wouldn't be clear exactly how to compute this integral. So there's no closed form solution. So there's always like this dance of you want to make your model more expressive, but each time you do that, you have like the cost of inference becomes larger, or like inference becomes more difficult. Okay, so that's always sort of the trade-offs that we are doing when people are developing these methods. So okay, we're gonna see essentially how to get around these problems in some cases. So we're gonna do approximate inference. So approximate inference generally refers to a variety of methods to go around these intractable inference problems. And there are general principles to do that. And we're going to see like two general principles to do it. But in general, like exactly how you're going to tackle a problem is going to be very dependent on the structure of the problem you care about. Like, so for different problems, you're going to use different tools, and the details of how you do things will change depending on the model you deal with. Okay? But still, you can sort of identify like broad categories of methods to do approximate inference. And so the two important categories that I'm going to talk about today is sampling methods and variational methods. Okay, so for sampling methods, there's a lecture after, so I'm going to be very brief and very succinct. So essentially, in sampling methods, what you do is you come up with an algorithm to sample from the distribution you care about. Okay, and this is like it's like random sample generation. and this is like a very rich field. There's a lot of literature on how to do that. I won't give the details of how to do it, but I guess the lecturer after me will give some of these details. For instance, you could use a GFlowNet to sample from your distribution. That would be like one way to do it. So I guess GFlowNet are sort of part of sampling methods in a sense. And so here, what I'm going to do is I'll just assume that you have a way to sample from a given distribution. Okay, so let's do that. So we assume that I can sample independent realization of my distribution px. Okay, so I'm going to call my samples x1 up to xn, and I'm going to assume that they are independent and identically distributed. And the whole point of sampling method is that now that you have those samples, you can estimate all sorts of statistics about your distribution. So essentially, this is called the law of large numbers. What it tells you is that the empirical average of those samples will converge to the distribution expectation, like the actual expectation of your distribution. And this will happen if you have sufficiently many samples. And for those who care, it's like almost sure convergence. But if you don't know what this means, it's really not important for our purpose. So this empirical average here is called the Monte Carlo estimator of the expectation. And you can also estimate all sorts of integrals with this method. I won't go into the details of this, but you can, looking forward to the next lecture. So this is the high level idea of sampling methods. Okay, does that make sense? Yeah, still good. Okay. Okay, so now we're gonna jump into variational inference as another way to do approximate inference. So variational inference is a specific instance of variational methods. And variational methods are sort of a broad category of approaches to transform a given problem into an optimization problem. So a first example of that is, so now we're sort of out of the realm of inference and even probability. We're just looking at variational methods as a whole. So one example of the variational approach would be to transform a problem of finding a solution to a linear system. And so you transform this problem into an optimization problem. So here it's quite direct to see that these two things are equivalent, right? So if you solve this linear system, you also solve this optimization problem and vice versa. So we have transformed the problem of solving a linear system into an optimization problem. Another example is with differential equations. So I'm absolutely not an expert on this, but in some cases you can transform the problem of solving a differential equation as a problem of minimizing a functional. So a functional is a function that takes as input another function, and you want to minimize this functional. So you try to find a function that minimizes this functional. And this is analogous to like Newtonian and Lagrangian physics, if you guys know what this is. Otherwise, it's not a problem. So what is interesting for us with this perspective is that when you see the problem as an optimization problem, this sorts of it opens up new strategies to approximate solution to the problem. Okay, so we're going to do that for inference now. So we're going to apply this logic of variational methods to the problem of probabilistic inference. So what we're going to do is we're going to transform the inference problem into an optimization problem. How are we going to do that? So to explain that, I will consider the example that I have introduced before. So you have this deep generative model. So again, PZ is just a Gaussian, and P of X given Z is Gaussian with a mean outputted by a neural network. And now we want to compute the posterior P of Z given X0, which we saw was intractable. So the idea would be to minimize some sort of distance between distribution. This is called the KL divergence. It's defined as such. You don't have to understand like the details of exactly like what this means. You can try to think about it, but the idea is that this is almost like you can think of this as a distance between two distributions. So it's not exactly a distance, but it's almost like a distance. And so you have this nice property that this function is always bigger or equal to 0, and it's 0 if and only if both distributions are equal. And what we're going to do is we're going to try to find a distribution Q which is as close as possible to the posterior that we're trying to estimate. And what we're going to do is we're going to pick this this family of distribution to be simple in a way that like this minimization problem becomes tractable. Okay? Because of course, if you don't constrain this the family of distribution over which you optimize, the solution to this problem is just to like set Q to be P of Z given X0 to be the posterior. And of course, it would mean that like this optimization problem is as hard as actually computing the posterior. So what we typically do is we pick a simple family of distribution to make our life simple. So that's what we're going to see. But of course, it's not clear how to actually perform this minimization because P of Z given X0, the thing that we don't want to compute, actually appears in this expression. So how do we compute this min? How do we minimize this expression? So this is what we're going to do. So here's the trick. We're going to rewrite this KL divergence in a nice way. Okay. So here in the first equality here, I'm just applying the definition of what is a KL divergence. Okay, so I can write it as expectation of log QZ minus log P of Z and X0. So I'm just using a simple property of logs. And here I'm using the definition of a conditional distribution to go from this line to this line. So essentially, like this is the numerator, and this is the denominator of this conditional. Okay, and again, I apply property of logs to like break it down into a sum, and I get this. And now I sort of regroup terms in a useful way. So I will group these terms together. Essentially, when I take the expectation of this term, I get the KL between QZ and PZ. Here, essentially, I do nothing, right? I'm just using the linearity of expectation. I get this term here. And since this term here does not depend on Q, I can just put it out of the expectation. Okay, so now I have this new expression, which happens to be equal to this one. And the nice thing here is that, first of all, this term does not depend on Q. So if I want to minimize this, I can just work with this term, right? Because this is just a constant. So I can forget about this. I can just minimize this with respect to Q. And what we're going to do is we're going to pick the family of distribution to be nice in a way that I can actually minimize this. That's kind of the trick. And this is like a very general idea that you can apply in all sorts of settings. So you might have noticed that I haven't used the specifics of the deep generative model that I have shown before, right? I'm talking about this. Like I haven't used like this, right, in my derivation. So it works for any inference problem almost. And so that's a very general idea. But like the devils are in the details. So the devils are going to be about how do we choose this family of distribution so that this problem becomes tractable. So to illustrate that, we're going to sort of build towards the variational autoencoder. So many of you might already know it, but yeah, we're going to see it now. So in order to get to the variational autoencoder, 3 ingredients are missing. The first one being, as I said, we have to choose this variational family Q. And we're going to see also that variational autoencoders are performing amortized inference. And we will also see how to actually learn the parameters of the model. So yeah, that's what is ahead of us. So any questions so far? Everything's clear? Don't be shy. Okay. Okay, so in the vanilla VAE, we take the variational family Q to be the set of Gaussian distribution with a diagonal covariance. In other words, we take Q to be of this form. Okay, so simple distribution and diagonal covariance, very simple. Of course, in general, the distribution that we're trying to approximate won't be Gaussian. Okay, so it means that when we perform this minimization, there will always be like some gap. It's only an approximation. We will never be able to get exactly the right posterior. So that's why we have this inequality here. But okay, so we won't be able to get exactly the right posterior, but at least it will make our problem tractable. So that's kind of the trade-off here. Okay. Okay, so amortized inference. So in the way I formulated things so far, essentially for each sample xi, when I'm estimating P of z given xi, I have to solve this minimization problem, which we saw is equivalent to this one. Right, so now I have a bunch of i's floating around, right? It's just that for each sample xi, I have to perform this minimization to estimate my posterior. So I have to fit qi for each sample xi. So in amortized inference, instead of doing that, we are essentially parameterizing the relationship between x and the parameters of q. So let me say that again. So essentially, we will learn a function that takes xi and outputs the parameters of qi. Okay. So usually it's a neural network. Okay. And the reason it's called amortized inference is that we pay we pay a fixed cost, right? So we just pay the cost of having one neural network, and then I can add samples, and I don't have more parameters adding to my model. Whereas if I stick with this formulation, for each new sample, I have to add the parameters of qi, which are essentially the mean and the covariance. So that's why we call it amortized inference. We sort of amortize the cost over samples. And so yeah, precisely what we have now is q of z given x, where the mean is outputted by some function of x, and this function mu z is going to be a neural network, and similarly for the variance. Okay. So that's the idea of amortized inference. Does that make sense so far? I mean, yeah, details are sort of coming shortly, but yeah. Okay, so we went from our original variational inference problem, where we had to perform this minimization individually for each I, to this amortized inference formulation. So now we can ask, okay, how am I going to perform this maximization? And what we're going to do is simply apply stochastic gradient descent to do that, to optimize the parameters of my Q of Z given X, the parameters of those networks. So remember, like mu Z and S are the neural networks used to output the parameters of my variational posterior. Okay, Q. So I want to optimize those. So how am I going to do that? I need to be able to compute the gradient of the loss, of course, if I want to do gradient descent. So it turns out that this term is easy to deal with because we chose Q to be a Gaussian and P of Z is also Gaussian, you have a closed form solution for the KL. Okay, you can actually write it down. And to compute the gradient, you can just apply automatic differentiation to that expression. So that's good. We can compute the gradient of this term. This term is a little bit more tricky because we have this nasty expectation here. And we cannot really bring the gradient inside the expectation here because we're taking the gradient with respect to parameters of Q here. And so yeah, it makes your life a little bit harder. So to get around this problem, we're going to apply the reparameterization trick, which we're going to see now. Okay, so reparameterization trick, what is it? So we're going to rewrite our sample Z in this form. Okay, so the idea is Z is sampled from my distribution Q of Z given X, if and only if Z is written as such, where epsilon is some white noise, some Gaussian noise here. So it's easy to check that this is true for Gaussian. When you notice that, it allows you to rewrite this expectation in this form. Okay, so what happened here? Now my expectation. So here my expectation was with respect to Z. Now my expectation is with respect to epsilon. And what I did is I replaced Z by its reparameterized form. Okay, and okay, so those two expressions are equal. Now I can try to take the gradient with respect to the parameters of my neural networks. And what happens here is that because now I have like epsilon here, which does not depend on the parameters, I can just bring the gradient inside the expectation. And yeah, this gradient can be computed using automatic differentiation, and you can estimate this this expectation using Monte Carlo estimation. Okay, so that's the trick, and it works for not just Gaussian, but for also all sorts of other distribution, as long as you can reparameterize it in a similar way. Yeah, question. Can you maybe? Oh yeah, okay, yeah. So say that again. I will repeat your question. Yeah. No, it's fine. It's fine. You can sit. I'll just repeat your question. Yeah. Yeah. So yeah. So there is, like, I'm skipping a lot of mathematical details here. Like, of course, if you want to swap. Oh yeah. I have to repeat the question. Okay. So the question is, why can I swap the gradient and the expectation here? The person in the audience said that we have to check conditions like dominated convergence and things like that. Of course, I'm skipping a lot of details here. When you swap a limit with an integral, there are all sorts of details that you need to worry about. I'm not worrying about this now. This is fairly standard, so I guess trust the common wisdom. But of course, like if you wanted to be super rigorous, you would have to check those conditions. But for now, we don't have to care about it. But the point is that you clearly couldn't do it before, right? So because the expectation is taken with respect to a random variable that depends on the parameter with respect to which you're differentiating. So that's where like things break. So, but you're right. Like if you wanted to be rigorous, you would have to check that you indeed have a right to swap these operators. Okay. Okay. So let me just step back. So I showed you that we can compute the gradient of this expression. Okay, so it means we can perform stochastic gradient ascent in that case because we're maximizing to perform my inference. Okay, my approximate inference. Do I have to say something more here? Yeah. Okay. So all of that was just about inference, right? Just about estimating P of z given x. I haven't talked about how to actually learn the parameters of my generative model. So that's what I'm going to discuss now. How do we learn? Yeah, okay, so that's what I said already. Now we investigate how to estimate the parameters. So if you're trying to learn parameters for a model, the first thing to think about is like, can I just do maximum likelihood estimation? At least that's what I'm thinking about always. And so if you want to do maximum likelihood estimation, you have to compute you have to maximize this log probability, right, with respect to the parameters of your model. It just turns out that for this more involved model, this is hard to do, right? Because if you write down this log p of x, you'll have like again an integral with like a nonlinear function, and it's not clear exactly how to compute the gradient of this thing. So what we're going to do instead is we will maximize a lower bound on this log likelihood. Okay. So let's see how to do that. So here I'm just reusing some computations that we saw before. So earlier we saw that we can write this divergence between q of z given x and p of z given x in this form. Okay. So it's something that we already saw. And what I'm doing here is I'm just using the fact that the KL is always bigger or equal to 0 to get to this inequality, to this lower bound, right? So if this guy here is bigger or equal to 0, I can sort of take these two terms and like send them on the left hand side of the inequality, and I get this inequality. Okay. So that's a lower bound on my log likelihood. So and this term is called the evidence lower bound, the elbow. And so turns out that this bound is tight when of course when the variational posterior q of z given x is equal to the actual posterior p of z given x. But as we said, like because we've made simplifying assumptions about the posterior, we might not be able to get this equality as we saw already. And so to maximize this lower bound, we're going to take the gradient with respect to the parameters of the generative model P, which is essentially the parameter of your neural network here. And so to maximize the elbow, essentially, and yeah, I didn't mention that, but this is exactly the same thing that we were maximizing to perform inference before. And so I'm talking about like these two things as they are in a sense in a separate way, right? I'm talking about inference, so computing q of z given x, and maximizing the likelihood of my generative model. But you can actually do both of these things simultaneously. You can just maximize this lower bound with respect to both the generative model P and your inference model Q. And that's what we do in variational inference. In variational autoencoders, I should say. We just maximize this lower bound with respect to P and Q in the hope that this is going to push up the likelihood. So it's sort of like, yeah, a way to do maximum likelihood. And this is very similar to expectation maximization, which is a classical algorithm. Except in EM, usually what you do is you alternate between optimizing with respect to Q and optimizing with respect to P. And in some cases, you have closed form solutions to that. So you just alternate between optimize with respect to Q, optimize with respect to P, you alternate like that. Here we just do everything together, and we optimize with gradient descent instead. So that's VAs. That's the perspective. So yeah, I'm done. So yeah, maybe before doing a recap, like any questions on this that was clear or no? Okay. So yeah, okay, to conclude, we saw what probabilistic inference is. We saw simple cases of exact inference. Then we saw more subtle cases where computation is more challenging. We saw sampling methods as a way to sort of go around these computational difficulties. We spent some time talking about variational inference, and we built up to variational autoencoders, which is like a very popular method these days. Well, maybe not as popular as they once were, but it's a classic method, I guess. So yeah, if there's no more questions, I guess I'm done. Thank you.
Thank you, Sebastian. Is there any question for Sebastian? Last questions that's about probabilistic inference? No? Okay. So that's it for the sessions for this morning. So thank you for attending. We are going to be back at 2 p.m. This afternoon for 2 new sessions on sampling, and reinforcement learning. So yeah, have a good lunch.
So Merci. All right, so the food is back there in the corner. I highly recommend random access. Let's just not, have a queue of 150 people. Just go for the food. That's going to be more efficient.
Okay, Mike Dur online. Mike R online. Yes. Micropodium online. Mike 3 online. Mike Dur in the room. Hey. What?
Yeah, my Mila de Quebec only receives emails from other Mila de Quebec people for some reason. Extremely annoying.
Yes. Hello, everyone. Welcome back from the lunch. I hope you got some energy, and we continue our day with sampling methods. And yeah, today we have Pablo Lemas presenting sampling methods for us. Pablo is postdoc researcher at Mila and several other universities, which I forgot. Sorry, Pablo. But yeah, I'm very curious to listen to you about sampling methods. Yep, the floor is yours.
Yeah, thanks. Yeah, I have a lot of an unfortunately large number of affiliations, but it's okay for Sasha not to remember them. Yeah, so thanks for Sasha and everyone else for having me and for inviting me to talk about sampling methods. So yeah, my background, so I'm in UDM and I'm in the astrophysics group. So my background is in astrophysics. And I'm going to talk about sampling methods, drawing a bit from examples from astrophysics. And I'll try to justify why I think that the astrophysics community and the cosmology community, which is a branch of astrophysics, have developed some of the best MCMC and so on methods. And I think it's because of the nature of the problems we're trying to solve. I'll also mostly talk about continuous problems, again, from experience, but basically everything I'll say applies very naturally to discrete problems as well. Right, so this should follow up from, continue from the talks by Tristan and by Sebastian this morning, in that they kind of set up the framework for probabilistic problems, and now we have a probability distribution. We're trying to generate samples. So, not working. Yes, it is. Okay. So I'm going to try to first make it clear what the problem it is that we're trying to solve. And the reason I'm going to be quite obvious to most people on this is that I've had kind of lost in translation situations with people, especially who come from machine learning, on what is it that we're trying to do here. So I'm going to adopt a Bayesian framework. So you wouldn't have to do this for my part of the talk, for the sampling part. But I think it's just nicely consistent with what came before. So you have some prior P of X, that's your prior knowledge on the parameters you're interested in. And you have a likelihood. So you've observed some data Y, and now you want to update your P of X to a P of X given Y through Bayes' theorem using the likelihood. So just to be on the same page, is there like something to point with? In that equation, basically, the thing on the left, we're going to call the posterior distribution. The thing on the top, P of Y given X is the likelihood. P of X is the prior. I think we'll have a pointer coming. And P of Y in the bottom, thank you. That works. P of Y in the bottom is what we call the Bayesian evidence or marginal likelihood. It was mentioned by Tristan, by other people before, and it will be important later in the talk as well. So just keep this equation in mind. Bayes' theorem, I think, has been in every talk so far. I'm sure there will be in more talks in the future. So here's an example distribution that we might want to sample from. And I'm going to show in orange potential samples you could get. So this obviously would be wrong. So you would have missed one of the modes. So that's bad sampling. That's also bad sampling. You've captured both modes, but you haven't fully modeled the modes correctly. You haven't reached the peaks. So it's bad sampling. But importantly, and this is a thing where I've had people disagree on what we're trying to do, this is bad sampling as well. So here you have captured both modes. You have sampled the peaks very well. So you have the maximum of both modes really clearly. But this is not what we're trying to do, right? And I think the reason that, again, this might be obvious to some people, but the reason why there's sometimes misunderstanding is that if you're trying to, I don't know, come up with something to play chess or, design a drug, you want the best, you want the peak, you want the best solution. But in this kind of problems, and Tristan mentioned self-driving cars as an example, I'll draw from astrophysics for other examples. You want the whole distribution. You want to understand the shape of the whole distribution really well. So you want this, right? That's the target. And anything else, so this we would call overconfident. You've misunderstood how wide your errors should be. Right. So cosmology. This is the example that I draw from because it's my background, but also I think it's pretty fun. So maybe you'll also learn something that you didn't expect to learn today. So in cosmology, the overall problem we're trying to solve is the following. You have a model that parameterizes the evolution of the universe from initial conditions till the large-scale structure we see today, so to galaxies, basically. And that model works with only 5 parameters, which is actually quite remarkable. So basically, when you specify, this is basically the density of what you could call regular matter, matter that we know from Earth, and dark matter. You specify the Hubble constant is the expansion rate, and you specify some things about the initial conditions, which are physics-based. You can then basically generate initial conditions and simulate all the way from the Big Bang all the way till today. So the problem we're trying to solve in cosmology is to do inference of those parameters. We want to understand those parameters. And again, I'll make it clear, we don't want the best value. We want to understand how well we can measure them. So the nice thing about working in this field is that you get pretty pictures all the time. So in this one, you don't see it super clearly there. It will become more clear. You start with initial conditions, which is a Gaussian random field, and you let gravity do its thing. So it's going to start collapsing. There will be overdensities in the initial field. It will start collapsing, and eventually you will start to see the cosmic web, hopefully. Maybe on the TVs it's more clear. In my screen, it looks very nice. The slides are available, so you can look at it more clearly later. But basically, the thing is that gravity will start collapsing things, and eventually you will get something that looks like the cosmic web, which doesn't. This one looks maybe better. So the point here is that when you change the value of these parameters, the universe starts to look different. So it might look more clumpy. It will have maybe more galaxies. So in the cosmic web, when the nodes of this web is where galaxies form. So when you see galaxies, you're kind of looking at the nodes of the cosmic web. So again, the problem is an inference problem. You're trying to do inference of these parameters given these observations. And so because the model goes from basically the very beginning of the universe till today, you can look at the universe today, you can look at galaxies. You can also look at something called the microwave background, which is an observation of the universe very early on. These days, you can even look at gravitational waves and things like that. And the problem you're trying to solve, again, this is just an example. Everything I'm going to talk about is more generic. But the problem you're trying to solve is, given an observation Y, you compress it in some way. Now you fix the parameters, so you pick how much dark matter there is, the expansion rate, and so on. You make a prediction for this data. And this data, you may not be able to see super clearly, but it has error bars. So you have an understanding of your uncertainty in these data points. And so you're playing the game of changing these parameters, and that changes your predictions until you find good fits. And you end up with things like this. So you might have seen this in other fields. So this is 1 and 2 sigma contour, like 68, 95% confidence levels of these different parameters that I was talking about before. And the point I wanted to drive home here with this example is that the reason that we care, we don't just care about the middle of this, we care about the whole thing. And the reason we really care in cosmology, and the reason that cosmology has been really good at developing MCMC methods, is that we can only see the one universe, right? So if you're particle physics, you can just redo your example. You can be a frequentist, you can just do your example 1,000,000 times and just do really bad statistics, and things will work out because you have enough data. But in cosmology, we have the one observation. So we have to really, really get the most out of it. So sometimes these error bars actually represent the limit to what we'll ever get to know from this one data point about these parameters. So it's important. We don't just care about the peak of the distribution, we care about the whole distribution. And in fact, this kind of degeneracies that we call them tell you, for example, that perhaps you cannot measure one parameter, you can only measure some certain combination of them. So there's physics and there's interesting science in there. Right, so that's my motivating example. And then I'll start talking about how you actually do this. Okay, so you have some kind of distribution you can evaluate. Now you want to generate samples. How do you do that? And perhaps the simplest way of doing it is with rejection sampling. So rejection sampling, I think, is the simplest. Maybe there's something simpler, but I don't think it gets much simpler than this. So in rejection sampling, so this is back to the target distribution we had before. What you do here is you're going to randomly sample your prior. You're going to generally sample X, and you're also going to randomly sample P of X. So you're going to get points that basically populate the space. And all you're doing now is you're going to select the ones that are under the curve. So you're going to reject, that's the name, the pink ones in this case, and you're going to keep the red ones. And then when you do a histogram of those, you get with something that looks pretty good. So that works. Rejection sampling does work. But you can probably already think that if I had a very, very small mode, I'm very unlikely to hit it by rejection sampling. And if I had multiple dimensions, this is going to scale horrendously bad. So that's the reason that no one ever in practice uses it. But if you have a simple enough problem, why not? The thing people use in more practice is MCMC. So that's Markov chain Monte Carlo. I've talked to people, especially people perhaps younger than myself. So my PhD was mostly doing MCMC. And I feel like there's sometimes younger people have only heard about MCMC in the context of, MCMC is so bad. We have to come up with something better because MCMC is terrible. MCMC is good. MCMC is good in the right problems. MCMC is not a multi-use tool, but in the right problems, MCMC is good. MCMC does what MCMC is supposed to do. So I'm trying to convince you of that. So the key thing here in the name is Markov chain. So Tristan already introduced the concept of Markov chain, and he knows Markov chains better than me, but I have a slide as well, and I made a pretty picture, so I thought I would keep it. And a Markov chain you just define by a state space. So just a bunch of states. In the case of my drawing, just 3. Some probability to go from one to another. And the fact that these probabilities are don't have a memory, so they don't remember what came before. That's called the Markov property. And the kind of Markov chain we're going to be interested in is one that is reversible. So it has a stationary distribution. So if you let it evolve for long enough, it will reach some kind of stationary distribution, some probability of S1, probability of S2, probability of S3. And it's satisfied what's called detailed balance. So that just means that the probability of S1 times the probability of jumping to S2 is equal to the opposite. I'm mentioning that here because it's important for Metropolis Hastings, which is what I'm going to talk about next. But also it's important to GFlowNets. So that will come up tomorrow, I suspect, when people start talking about GFlowNets. All right, so Metropolis Hastings is one example of MCMC algorithm. It's probably the one you've heard about before because it's the most commonly used. And it's an algorithm that has a lot of literature. So you will find a lot of tricks, a lot of implementations, and so on. And again, for the right type of problem, it works perfectly. So the idea is that you're going to create a Markov chain like those ones where the stationary distribution is going to be equal to your target distribution. P of this should actually be x given y there. So you start with some initial point, x0. If you have knowledge of your target distribution, you can pick it wisely. You don't have to. And then you start with a proposal distribution. So that's going to be a way to go from x0 to some other point. So in this case, in a continuous example, you often do some kind of perhaps a normal distribution around x0 with some standard deviation. If you have a discrete problem, for example, you might have a sequence and your proposal might just be changing some characters in your sequence or something like that. The proposal would just affect the efficiency of the algorithm, but the algorithm will, over infinite time, work even with a really bad proposal. And then all you do is you propose points from this proposal distribution and you accept it with that probability. And that probability just means if your proposal took you to a point of higher likelihood, you accept it immediately. If it took you to one of lower likelihood, you can still accept it. And the probability to accept it is just the ratio of the two. So you have here a little animation. So in this animation, the red arrows are going to be rejections and the green are going to be acceptance. And you can see there that all that you do is you just generate randomly. Your proposal here is quite broad, so you reject a lot of points. But all that happens from that is not that you get biased inference in any way. It's just that you're wasting a lot of computing time in bad proposals. But the algorithm works, and if you let it run for long enough, you will have this stationary distribution, which is this banana in this case. And so you will have samples from this distribution. Tricks to make it work better. The most obvious one is to change your proposal to make it better. In a continuous case, you often can learn, for example, some kind of covariance matrix. You can even use deep learning here. So I'm not going to have deep learning in general in this talk, but I have seen implementations where you use deep learning to propose points. The thing with tuning the proposal is that if your acceptance risk is too high, you're going to walk this distribution really slowly. If your acceptance risk is too low, you're going to just spend a lot of time rejecting points. So I don't think there's a hard rule, but in my personal experience, practitioners aim for like a 0.3 or so. So you accept 1 in 3 points. That works relatively well. And again, the easiest way to do it is to just somehow learn a covariance matrix here that adapts to aim for that 0.3 acceptance rate. So that's pretty easy to do. You often use multiple walkers. You might have heard the term walkers. The term walkers comes from the fact that you're just walking around this distribution. If you have multiple walkers, that has multiple advantages. First of all, you generate samples in parallel. But more importantly, there is this calculation, which is called the Gelman-Rubin diagnostic. And Gelman-Rubin will basically tell you if the stationary distribution that your multiple walkers have reached is the same. So it serves as a stopping criterion. It tells you when you can stop sampling. And finally, you might have heard the concept of burn-in. So imagine in this case, this is multimodal. I'll talk about multimodality later, but ignore that for now. Imagine you start in a bad point here where the likelihood is very low. Your MCMC will eventually take you to one of the modes, and then you start moving around. So if now you plot the probability, actually this will be the minus probability. It starts really low. Again, this is minus probability, bad labeling. And it very quickly drops, and then it just stays pretty stable. So this means you've reached the stationary distribution. These points are points here before you reach stationary distribution. So you should not keep them. They're not really samples from distribution. So what people do is burn in some of your chain. So just remove some of the points which were before the stationary distribution. There might be a hard rule on how to do this. In practice, I think you can just eyeball it pretty easily. And I wanted to mention an implementation that I quite like. So there's multiple. There's one called MCE. I don't know how you pronounce it. But this one is one that was made by cosmologists. But you can actually use it for anything. So it has all of the tricks, like adapting proposal and Gelman-Rubin convergence and so on. It's written to be parallelizable as well. And it was written to be in cosmology. So the short name has cosmology in there. But actually, you can just put any likelihood in there. And in fact, we recently had a paper with Sasha and with other people, some of the organizers, where we compared GFlowNet. Sasha can talk about this paper later in the week. But we compared GFlowNet with MCMC, amongst other things. And the MCMC part, we use this cosmology code. So you can just put a molecule likelihood, and it works just as well. So that's one of my MCMC runs for ibuprofen. Again, Sasha will talk more about this paper. And if you're interested in using this code, you can find it online. You can talk to me as well. That's Metropolis Hastings. So that's probably the most commonly used MCMC method, but there's others. So this one is called Metropolis Adjusted Langeable Algorithm, or MALA, if you shorten it. So this one you can use only if you have access to the gradient of the likelihood, the gradient of your target distribution. So if you have differentiable programming and you've written your target distribution differentiably, you can use this. And you've probably heard of Langemann dynamics in terms of diffusion and so on. It's a similar idea. So you're going to start with a point. You're going to propose a new one using Langemann dynamics, so something like Euler-Maruyama or something like that. And then you can calculate an acceptance probability similar to the Metropolis Hastings one. That is going to give you the right stationary distribution. So again, the penalty is that you need the gradient, but it actually scales better than Metropolis Hastings. So if you have gradients, you can use that. Or you can use Hamiltonian Monte Carlo, which is pretty similar. In fact, I think there's some papers that say that fundamentally they're kind of doing the same thing. It gives you much nicer animations. By the way, they're not my animations. I found these online and they're amazing. You can play with it, and I wasted much more time than I should have playing with this. So this is Hamiltonian Monte Carlo. So people with a physics background will be familiar with Hamilton's equations. Hamiltonian Monte Carlo is a similar idea. You start with a point, you create like a fake momentum actually variable, and you also assign a mass matrix, and the mass matrix is a hyperparameter of this algorithm. And then you have a mass, you have a position, you have a momentum, so you just solve Hamilton's equations, which basically do dynamics, where in this case the potential is going to be minus log probability. And you can show that will also give you the right stationary distribution. Again, scales much better than Metropolis Hastings. So some people in the astrophysics community have used this in many thousands of dimensions. I'm sure this also happens. I mean, I think there's even BNN papers doing HMC. So it scales to very high dimensionals pretty well. It's not that good at mode finding. I'll talk about that later as well. But yeah, the idea is that the tricky thing here is to tune the mass matrix, but if you can do that, it works really well. Another hyperparameter is the length of this trajectory. So you're solving dynamics here, and the length, if it's too short, you end up with a random walk, and if it's too long, it becomes really inefficient. There's a variation of the algorithm called the no U-turn sampler that automatically tunes the length. So there's also very good implementations of all of these. And yeah, that's MCMC methods. So now I'm going to talk about another type of method, which is called nested sampling. So nested sampling is something that we use a lot in astrophysics, and it's not very well known outside. And I think it's a pity because it's a really good algorithm for, again, for the right problems. It's not going to, I'm not saying drop GFlowNets and do this. I'm going to justify that. But for the right problem, this is a really, really good algorithm. And let me justify it. So there's two reasons why it's good. The first one is multimodality. So MCMC does not do multimodality. That applies to HMC, to all of this. And the reason for that, you can kind of see it. Imagine that I'm solving this multimodal thing. So I'm trying to cover these modes. And I start here like before. And this animation now is going to give me the MCMC. So I go towards the mode. I sample it. Now there's a non-zero chance that I'm going to take this jump. But it's a very small chance, right? Because there's a small probability of going towards smaller likelihood, but I have to do multiple of those to hit another mode. And then I would have to do that again and again. So over infinite time, MCMC will cover everything. Over practical times, it will not. So MCMC is really bad for multimodality. It basically, in practice, gets stuck in modes. So a solution to this is nested sampling. The other reason why you can use it is to calculate the Bayesian evidence. So if you remember before in Bayes' theorem, I mentioned that the denominator is called the Bayesian evidence, marginal likelihood. And you can also rewrite it by very simple algebra as the integral over this, just to enforce that this is normalized. And so the original reason nested sampling was created was to solve this integral. So this integral can be very high dimensional, it'll be as high dimensional as X. And it's intractable in principle, but in practice, there's a trick to be able to do it. Let me tell you a bit about why you want to find that integral in the first place, right? Because it's been mentioned that there's this Bayesian evidence, and we've so far kind of neglected it. And in fact, if you just want samples, you probably only care about the ratio of these between samples. So you don't actually care about the normalization. But the normalization has important information as well. So Tristan mentioned coin flips. I'm also going to draw on coin flips as a classic statistic example. And so the main reason people use the Bayesian evidence is to compare models, right? So imagine that I've done a bunch of coin flips and I have two models. One is that my coin is biased and one is that it is not. So what I want to know is what is the likelihood, what is the ratio of the probability that my model, of model one, I'm biased given the data, to model two, which is biased given the data. That's the kind of Bayesian way of solving this problem. And now I'm going to do some very, very basic algebra, so bear with me. So you can write Bayes' theorem for either of these ratios, pretty straightforward. And then you can actually take the ratio. You end up with those two terms there. And what you're going to notice is that we have P of D here and P of D here. Those do not depend on the model, so those go away. And so you end up with something like this. And now here you have this ratio P of M1 to P of M2. So that would be it would basically be the prior probability you have on each model. So how much more likely do you think one model is with respect to the other? So if you're assuming that you're going unbiased yourself, if you think that they're both equally likely, that means those are the same. So those also go away. And therefore, the ratio that you want is the ratio of the Bayesian evidences. So if you calculate the evidence for each one of these models and you take the ratio, that's going to tell you which one is more likely given the data that you've seen. So here's an example more interesting maybe than the coin flips, marginally only, which is I've seen this data, f of x, and I'm going to try to fit it with a model. And my different models are going to be polynomials of different orders now. So order series is going to be a horizontal line. And here I'm going to plot, I didn't label this. It's the first time I use this slide, so there's a lot of bugs, but there should be a set here. So this is going to be the evidence. Okay. So order 0, that's just a line. So that's my best fit. That's the evidence there. Not very good. Now I take a second model, which is model 1. So that's an order 1 polynomial, slightly better evidence, so slightly preferred. Quadratic. So that now has 3 terms, so it's a little bit more complex. The evidence goes up. It's a third order. As it turns out, perhaps whoever designed this problem made it third order. So it fits perfectly. So the evidence really peaks. And now here's where the evidence, the Bayesian evidence and the Bayesian way of doing model comparison becomes really cool, is that Bayesian model comparison will penalize unnecessary complexity. So when I go to order 4, what's going to happen is that my best fit, because again, I designed this to be a third order, the fourth order coefficient is basically going to be 0. And what I'm going to have is that now I have a parameter which actually I don't need. So that model gets penalized. It gets penalized because it has more parameters than I actually need. I have enough with 4 parameters. So I don't need the 5th. And if I do a 5th order polynomial, I get penalized even more because now I'm adding an extra parameter that I also don't need. So the point of Bayesian model comparison is that it will give me the best model with the least necessary complexity. And this is something that, again, perhaps not usable for every discipline, but again, back to the astrophysics example, and I'm sure there's many others in other sciences. I don't want a model of the universe that is adding a parameter there that is unnecessarily complex. I want to create a model as simple as possible. And in fact, people who are into philosophy might have heard of Occam's razor. People often refer to this as the Occam's razor penalty as well. Don't love the term, but if you like this kind of stuff, by the way, this part of the talk and a lot of my talk is inspired by this book, which is excellent and I really recommend. And another way that you can use the evidence, this is a bit of self-publicity for me. I'm still a postdoc, so I have to do publicity every time I can. Is you can use it for another problem, which is, imagine now that I have 2 observations. So we came up with this in the context of astrophysics as before. Imagine I've seen the universe with the microwave background and with galaxies, and I have a model that is supposed to explain both. You can use the evidence to tell you how likely it is that both of these observations would come from the same model. And the point is that if that's very unlikely, that means that your model is probably wrong, so you need a new model. So we came up with a way to use the Bayesian evidence to quantify this. If you want more, I have a link to paper there, but if you want to hear more about that, you can talk to me later as well. Right, so that's why you use the Bayesian evidence. But now let me tell you about how I actually calculate it. Because it does remain a very high dimensional, difficult integral. So nested sampling relies on the realization. So you have a prior distribution. In this case, it would be this box. And you have a likelihood that you can evaluate. And nested sampling comes from the realization that every point defines some volume, which is the volume of all points with higher likelihood. So in this case, this point here defines this volume. And so what you can do is you can take your horrible, very high dimensional integral. In this case, it's 2 dimensionals. It's not so bad, but imagine that it's higher. And you can now basically rewrite every x in terms of this prior volume. So this prior volume will go from 1, which is when you have the whole box, to 0, which is when you've reached the maximum of the distribution. Again, this is the volume that is higher likelihood than the current point. And so you can turn this very high dimensional integral into 1-dimensional integral, which is from volume 0 to volume 1, the whole box. So all you need is a set of points of increasing, monotonically increasing x, or monotonically decreasing, which is in fact what we're going to do. And then you can just rewrite this integral as a quadrature. And you're done. So the way the algorithm works is you start this result integral that you want as 0. Now you're going to pick the lowest likelihood point. So you generate a bunch of points from the prior, and you call those the live points. And I don't particularly like this name, but I didn't come up with the algorithm. You pick the lowest likelihood point, and you're going to replace it with a point that has higher likelihood. So basically, you're going to sample this blob here uniformly, and you're going to pick a point from that blob. Again, uniformly. The uniformly part is key and is what makes this difficult, right? Otherwise, you could just take the gradient and go to the maximum, but you have to make it uniform. You're going to do that. And then if you really did a uniform, the amount by which you've compressed this volume, you can approximate like that. The details are in a bunch of papers, which I can point you to. And because of this quadrature that I have here, then you can update your set estimate like that. You repeat, and what's going to happen is that you're going to basically slowly converge towards higher likelihood regions because you're always replacing with a better point. And eventually you're going to end up with points concentrated on the higher likelihood. So incidentally, you can actually use this for optimization, and it works pretty well. But the key thing is that not only does it give you this integral, but also if you weigh these points appropriately, again, there's a bunch of math here, which I'm not showing, but you can look at the paper. you weigh these points appropriately, you actually also get samples from the distribution, which is what MCMC gives you. So you end up with both the integral and the samples from the distribution. The difficult thing here is that imagine at this fixed step, I have to uniformly sample from these 3 blobs. So that's pretty difficult. So you can think rejection sampling, that's the way the original algorithm was made. So you randomly sample points and only accept when the likelihood is higher. But obviously that's extremely inefficient, especially towards the end. Another method is to basically build ellipsoids around the points that you already have. That works better, not ideal. Slice sampling works really well. So the idea there is that you're going to build slices and you're going to bounce off the walls. Again, more self-publicity because still a postdoc, is this paper that we're going to put on the archive probably on Friday, I'm hoping. I've actually been delaying that, where we use the gradient of the distribution to do this task of sampling from this. So we use the gradient and we actually get really good performance. So you can see here nested sampling in action, right? So that's the truth. This is I don't know, like 20, I don't know how many modes. There's a lot of modes. You capture them all with the nested sampling. This is one that one of our PhD students in the group came up with, which is a really diabolical distribution, and you do really well. This is comparing with something called FAB, which is one of the state-of-the-art sampling methods using deep learning. Again, I'm not talking about deep learning methods here, because I think the best one is probably GFlowNet, and that's the whole point of the workshop. But we do much better than FAB. We actually capture the much better. And you can actually combine this with GFlowNet. So the paper will be on archive probably on Friday, which is convenient because that's when you will know everything there is to know about GFlowNet. So you can then go to the paper and see how you can combine these 2 things, but I will not spoil that. And I'm almost done. I'll end up with some more publicity. This is the last one, which is a paper that we had recently on checking how good your samples are, whether your samples are from the right distribution. So that one was on ICML, and yeah, I don't want to dwell on that too much. So I want to leave some time for questions. So I wanted to finish with a little metaphor, which is I want to make the point that GFlowNets are really good. I'm not anti GFlowNet, quite the opposite. I'm working a lot on GFlowNet myself, but you know the way I like to see it is, you know, GFlowNet is like a really, really cool tool that you can use for multiple things, like super nice and new and multifunctional, and we're going to hear about all the functionality. And MCMC is like a hammer, you know, it's just like an old-fashioned hammer. But, you know, sometimes just have a nail in the wall, and you could spend like a long time looking at your drill and come up with the right setting, but you just take your hammer and, you know, bang it a couple of times, and just it will do the work. So sometimes it's worth not reinventing the wheel, and for the right problems, MCMC, nested sampling, and these methods are just fine. So yeah, I've put my contact info there. My slides are here, and I think they're also going to be shared through the workshop website. And yeah, there's still sometimes some questions. So thanks.
Thank you so much for the excellent talk. Do we have any questions in the audience? Please go to the mic.
Yeah, thank you very, very much for your talk. Sorry, it's probably a stupid question, but I didn't really understand when you talked about Bayesian evidence. So you're doing the ratio,
yeah,
but the marginal likelihood is canceling out, right? So you don't really need the integral.
No. Sorry, this is not very clear notation on my part. So you have so here the notation is X is the parameters that I'm interested in.
Yeah.
And Y is the data. And I kind of changed notation, which is really bad. Again, this is the first time I use these slides. So this is good feedback. Y here is an observation that you have. So in the next slide, I'm going to call that D, which is really bad of me. So here, what you have is now you have the observation and you have models. So I guess implicitly, when you do this, there's also a model here on the right. You're assuming a model that has the parameters X. And so what you have now is 2 different parameters, each of which has, so here P of Y would, I guess, be the same as P of D given M.
Yeah.
And the one that cancels is P of D without given M. So it's just the probability of observing this data model independently.
Isn't this the integral? Because it's the marginal likelihood, the P of D, right?
It's the marginal likelihood of P of D given the model. It might be easier with a board, but there's a comma M here in everything. in that because I have parameters, there's an implicit model here that I'm assuming. So in the case of the coins, there's two of these, one for the unbiased model, one for the biased model. The unbiased model doesn't have any parameters, and the biased model has one parameter, which is the bias. So there is a P of Y given model 1 and P of Y given model 2. Again, might be easier to do this with.
Okay.
Yeah,
but
it's a good question, and it points out my bad notation here.
Okay. And yeah, I have a little question as well, again, on this thing as well. I didn't really understand and why polynomials with too much complexity were penalized.
Right. So again, you can imagine. Again, I always draw from astrophysics, but like you can imagine in any kind of scientific model, this is it can get philosophical, so maybe a human bias, but you prefer the scientific explanation that's the simplest, right? You prefer the scientific explanation that it's not unnecessarily complex to explain phenomena that you observed.
Yeah.
So the point of the Bayesian evidence is that, and this is in the nature of, you kind of, when you do this, the integral, which is not here, when you do the integral, if you have a parameter that's not adding anything, you're still integrating over the prior in that parameter. So it's going to add some penalty for that complexity that you don't need.
That's why, even though the loss is
so that's
going
why
down.
Exactly. The loss remains the same, but I mean, you can even do the book that I pointed out does the calculation for Gaussian posteriors, in that if you add a new one that's not doing anything, you have a term that is the ratio to on the maximum, and another one that's the number of parameters. So you basically, it's kind of similar to the AIC and the Bayesian information criteria and all these things, in that it will penalize complexity in that way as well.
Yeah, thank you. Yeah, I love this.
No, thanks.
Any other questions? Can go to the mic.
Got a question?
You mentioned about metropolitan Hastings sampling, and you mentioned that we have the gradient of the target distribution. Can you give an example how we can have that?
Yes, good question. No, Metropolis Hastings does not assume a gradient, but both the Langevin version and the Hamiltonian Monte Carlo version assume a gradient. And I mean, the example would be in this distribution. In the Metropolis Hastings version, you only have access to, if I give you a point, you can evaluate the value of the distribution. So it will be, very high here and not very high here. If you have the gradient, you can get the value, and you can also get an arrow that points you towards the maximum. So that would be the gradient. And if you have access to that, you can already see how that helps you simulate dynamics and get points that, because the gradient's pointing you to high likelihood regions, it helps you do the sampling a bit more efficiently. So it all depends on if, when you wrote this function, this p that you're evaluating, if you did it in a differentiable way, which may not be trivial if you have, I don't know, step functions and things. Does that make sense? Yeah. So I mean, again, it doesn't apply to discrete problems. You cannot take gradients there, but in this case, you can actually. I think the animation actually has gradient. The other one definitely has gradients. No, it doesn't. Again, so here you can imagine in one setting, if I pick a point here, I can evaluate P of X. In the other setting, I can not only evaluate P of X, but also the gradient of P of X, which again will be an arrow pointing, in this case, the maximum's here. So if I'm here, it will be an arrow pointing that way. If I'm here, it'll be an arrow pointing that way, and so on. So that gradient will give me information about how I should generate the new samples. But that's not something, before you had differentiable programming, you never had access to that. And even now, you may or may not have been able to write it in a differentiable way. And maybe you guys are, used to always having gradients, but my first time since it was in Fortran 90, so there was definitely no gradients there. There's one more, Sasha, I think, if there's time.
I imagine that depending on your proposal distribution, that sequential elements of a chain will be dependent on each other.
Yeah, that's a very good point that I kind of conveniently skipped. Yeah, so there's something called the autocorrelation time and so on. So basically, yes, if your proposal is too close, you will get points that are too correlated, and that's bad. And you can solve it, but ideally you just try to generate enough points that that's not an issue. But yes.
Tips or heuristics that you guys normally use.
I mean, there's actual calculations you can do on the kind of self-correlation of your chains, and you can remove intermediate points to decrease the self-correlation. But it's I can point you to literature if you actually have to. I should have actually probably added a slide on that. Yeah, thanks.
Following up on this, I expect that if you have multiple workers, they will be independent, right? I mean, they could be independent.
Multiple, that's another good point. To do Kalman-Rubin, the multiple workers have to be uncorrelated. There are implementations, including some very famous public ones, that use information of all the walkers to propose points. So that means that you can no longer use Kalman-Rubin because that assumes independent walkers. But normally, if your proposal is random, then they are entirely uncorrelated. Yeah.
If there's no interaction between the workers and you're just sampling in parallel, then I assume
then they're entirely uncorrelated. Yeah, and that's a condition to use Kalman-Rubin. Actually, I should have mentioned that they have to be uncorrelated.
Okay, maybe I also ask one question. You mentioned that like there are some problems which are easy to solve with simpler method like nested sampling, and we don't need to use GFlowNet. And I'm actually curious, what are the problems where nested sampling and MCMC really doesn't work and we need GFlowNet?
Yeah, that's a very good question. So, I mean, I think the nice thing about GFlowNet is that it's such a flexible framework, right? So like you have your application, but then Tristan talks about like hostile learning and all of these things, which MCMC, I mean, maybe if you really think about it, you might be, but it's really hard to use it for multiple things. From a pure sampling perspective, MCMC struggles with multimodal things. But if you do have something like HMC, it actually goes to high dimensions. So it's multimodality that kills you. If you have nested sampling, multimodality is no longer an issue, but scaling, because you're compressing in this way, basically the amount of compression steps you need will scale badly with dimensionality. So in our paper, we took it to like a few hundreds to like about 1,000 dimensions, but we haven't like, it's hard to take it beyond that, although it's still something we're maybe trying to think about, maybe with the help of GFlowNets or something like that. But yeah, so MCMC struggle with multimodality, nested sampling with very high dimension, like image kind of dimensions or above.
Thank you. One more question.
Is there any sampling method that we use like natural gradient?
That you use what, sorry?
Natural gradient, like second order.
Second order gradients, not that I know of. That's a good question. Not that I know of. You probably could use that. I mean, there might be. I wouldn't claim to know all that. There's a lot of sampling literature, but not any that I'm aware of.
Might be a stupid question, but for like both methods that require gradients, do we assume that we know the P of X that we want to sample from?
Yes, that's throughout this talk, we're assuming we know P of X. We have access to P of X. So we've learned it, or it has been given to us, or we know P of X.
Because that's not always the case.
No.
When that's not the case, like what's the alternative?
I mean, you have two options. You either separately learn P of X with like an energy-based model or something like that, and then you go back to this. Or you try to do it all in one go with something like a diffusion model or normalizing flow, and then you try to learn P of X and sample from it in one go. But this is assuming you know P of X.
Okay, let's thank Pablo again. And we continue with our next session on sampling with reinforcement learning, and is going to be presented by Padida Nori. Padida is a graduate student with Dorina Prekop, and yeah, very happy to have you here. The floor is yours, Padida.
Thank you. Hi, everyone. My name is Padida, and I'll give you, in this part of the workshop, I'll give you a brief introduction to reinforcement learning and its application to sampling. So what is reinforcement learning? What kind of problem does it solve? Reinforcement learning is for solving sequential decision-making problems based on interaction. So let's say in this example here, we have an agent, it's like robot, our agent here, interacts with the environment through its actions.
And then the agent receives some feedback from the environment in the form of reward and its observation. So the action will change the state of the environment and will transition to the new state. And the reward would be some scalar value that shows how good the actions are. And basically the goal of this agent would be to maximize the reward. So we will learn through this interactive loop how to take better and better actions. So I'll give an example here. It's our agent here would be a dog, and the dog. What's the goal of a dog? Tries to maximize the chance of receiving treats. So the people who have dog probably are more familiar with this problem. The actions in this setting would be different muscle contractions that a dog can take. And the dog will learn based on this interactive loop with the environment, basically its owner, that the certain muscle contractions leading to sitting will lead to receiving the reward. So our agent, the dog, will learn this. So now a more serious example would be basically a cool application of reinforcement learning for some real world problems, such as drug discovery. So in this setting, basically, we are trying to change some amino acids in a peptide. And through this action, we'll try to interact with the environment being our Petri dish. So in this example, let's say our peptide needs to have some antimicrobial properties, and these circles would show basically the circles will show the basically bacterial colonies. So when we interact with this environment, we add these peptides to this culture. We aim to see how the state of the culture would change. And we see the observation, which is the new state. And the reward would be, let's say, how effective the peptide was in inhibiting the bacterial growth. So through this interactive loop, we can learn what type of peptide we add to this culture to receive our desired basically biological property and maximize, let's say, antimicrobial efficiency here, the potency. So this was one real world example. We can go back, we're gonna go back again to this at the end of the presentation. So now to solve this problem, we need to formalize it, and that will be through defining the Markov decision process. So first, as we saw throughout the day, we heard about Markov chain, which Markov chain, we have a state and a transition operator, and we have this Markov property basically that our next state only depend on the current state. So it's like we forget about the history. And then we'll see in our Markov decision process, we have a state, we have actions and transition operator, which basically our next state not only depend on our current state, but also it depend on some action. And the reward would be when we go to the next state, what would be the reward when going next state upon receive an action. So the reward here is some scalar value. And here we will see the goal of basically reinforcement learning. That was a problem formulation. Now the goal of a reinforcement learning agent. So our objective is basically to find an optimal policy which maximizes the cumulative sum of rewards. So what is a policy? Policy tells us what action to take at a certain state. Reward is a scalar feedback that tells us how well that action was at a certain state. And here we are taking our expectations with respect to the trajectory. This trajectory is a sequence of state and actions, which we can see in this graphical model that like next state depend on the current state and action. And our policy gives us the probability of taking certain action at a certain state, okay? And the probability of this sequence of states and action is defined by product of our transition probability by our policy. So that was the goal of reinforcement learning agent. And we'll go back to this a lot of time into this presentation, you'll see. So one algorithm to solve reinforcement learning problems is called Q-learning. Q-learning is an example of a value-based method. So we saw again, the RL objective was to find a policy that maximizes the expected future rewards. And if we find our Q value as the expected sum of future reward, then finding an optimal Q value, when we find that, we can basically derive our optimal policy from that by taking the argmax. So in this algorithm, the optimal Q will satisfy the Bellman optimality equation, and we see how we use that as an update rule. In this pseudocode, we see the Q-learning algorithm, basically this in an interactive fashion, that at a certain state, we take action. In the most naive way would be basically taking the greedy action, taking an action that maximizes these Q values, okay? We interact with the environment, we receive reward, and then we go to the next state, and then we update the Q values. So our next estimate of the Q value would be our current estimate plus this TD error. So a good intuitive way to think about this TD error is that we are trying to basically learning guesses based on guesses. So thinking that all the future, let's say, action from now on would be optimal. Eventually, we try to basically our TD error should go to 0. And that goes to 0 when we find our optimal Q, with which basically fits into this Bellman optimality equation. So going back again to like what we saw in this algorithm is that we interact with the environment, we generate an action, we receive a reward, we go to the next state, and we update our Q values, and then we improve our policy by taking the argmax of the Q values. And then this loop repeats. So one important thing in this problem is trade-off of exploration and exploitation. As we said, that one naive way to find an action is to take the greedy action, okay? But what are the other things that we can, what are other things that we can do here? Because let's say if we always take the greedy action, there could be some part of the state space that we never explore. And that could be problematic, basically because maybe those states that we never visited were leading to high rewards. And because we never visited, we would not know. So we should have some strategy to balance this trade-off. So one way that Q-learning deals with that, the most simple method is called epsilon greedy. Epsilon greedy, what does it do? Is that it says with probability epsilon, take the random action, and with probability 1 minus epsilon, take that greedy action. Okay, and so again, I want to highlight that encouraging exploration is important because sometimes taking suboptimal action could lead to eventually a high reward. So we saw that was like one method to encourage exploration behavior. Another framework is called maximum entropy RL. Again, going back to the RL objective, the standard RL, the objective is we're trying to maximize the expected sum of future rewards. Okay, but what if we augment this reward with the entropy term? So the optimal policy that we will learn not only will maximize this reward, but also maximize its entropy at the visited state. So that would be good that this way the policy will learn some exploratory behavior. So this framework is called maximum entropy RL framework, and the benefits of this would be a better exploratory behavior, which is especially important in multimodal problems, better pre-training for later adaptation of the policy, and for robust reward control problems, which could be basically our policy would be robust to perturbation to the reward function. So these are some benefits of basically using this objective to derive the optimal policy. One algorithm that solves maximum entropy RL is called soft Q-learning. So this is very similar to the Q-learning that we saw before with some changes that we go through. So what did we do? We took we at certain state, we take an action. Before our action, let's say in the naive way, was taking the greedy action. But here, we would sample our action with respect to the softmax of the Q values. And then we interact same way like before with the environment, we receive reward going to the next state. And in the update step, instead of taking the max, we will take the log sum x, which is a basically, this is a soft relaxation of the max, the same way soft max is soft relaxation of argmax. So basically, this algorithm solves the maximum entropy RL objective that we saw in the previous slide. So now we will see what can be used this algorithm for. Some application of maximum entropy RL could be for sampling. In this example, I will give you an example of sampling peptides in autoregressive fashion, where our action space consists of 20 amino acids. Our state space is the sequence of amino acids of maximum 4. And our objective would be to generate biologically plausible peptides of length 4. So what do? We start from an empty string. We add one amino acid, like second, third, and then when we reach the length 4, we basically evaluate the reward. And each peptide is associated with a reward, which let's say in our example that we saw in the beginning, could be antimicrobial property of it. So we say that if we find the optimal policy solving maximum entropy RL objective, then following this policy, we'll sample the peptides, the objects that we want, with probability proportional to the exponential of the reward. Okay, so in this example, as we saw, we are sampling basically in some order, like in an autoregressive fashion, we are building a sample. But what if there was like no order in like basically building our sample? Let's say an example, it's like building a smiley face, which we add the mouth, the eyebrows, and at the end, we make an image of a smiley face. So in this case, it might not matter, like first adding the mouth and then the eyebrow, the final image might be the same. So what's the problem with this is that, let's say in this case, okay, we add the mouth and then the eyebrow and then the eyebrow, then the mouth, but we'll see that the final result is the same. So there are multiple ways to actually reach a certain state. So what do we do like here? You will see that maximum entropy actually doesn't give us the correct sample, doesn't sample proportionally to the exponential of reward. Okay, so how to solve this is to basically, we'll learn in the next stage of the workshop, there is an algorithm called GFlowNet, which basically addresses the limitation of the maximum entropy RL for this class of problems. And yeah, with that, I'll finish this presentation. And thank you everyone for listening.
Thank you so much, Badida. Do we have any questions? Yes, please, Lena.
you for the presentation. So here, what does it sample proportionally to if it's not exponential of R?
So it sample, if I heard correctly?
Yeah, so in this case, what does max entropy RL sample proportional to if it's not exponential of R? Is it like the number of trajectories multiplied by exponential of R or?
So yeah, the maximum entropy RL samples with respect to the exponential of the reward, but when we have like the order here being, let's say, autoregressively adding one piece of our sample. But in this case, because there are like multiple ways to reach that, then it's like biased, the problem. So the sample that we will receive with maximum entropy RL objective will be a biased sample. It's not correct.
Okay, and we don't know what is the reward in this case.
So the reward would be log of exponential of R. This is basically the reward, right?
Yeah, okay, maybe my question wasn't clear, but like if you don't have an order,
Mhm.
I mean, if you can have in any order, what will the policy be in the, I mean, what will the reward be in the end for if you train with max entropy RL? But maybe my question doesn't make sense.
Okay, the reward is basically we are using maximum, like the point is that we are not sampling correctly with respect to the something that we want, which is exponential of the reward. But yeah, we can maybe talk more. I understand better the question. Thank you.
Any other questions?
So you mentioned like some techniques to do exploration, so epsilon gradient and maximum entropy RL. Are there any other things other than these two techniques to do exploration in RL that we can use to improve some possible future rewards?
Okay, that's a good question. So I think yeah, there is other methods. Basically, one way would be like changing this like bonus here, like this bonus, like I said, in this case would be the entropy of the policy. Maybe we want to like induce novelty, but yeah, there are different methods to induce this exploratory behavior. Could be from some prior inducing this behavior through prior or yeah.
Thank you for your presentation. I have a question with respect to the AMB work briefly. So we know that biological sequences, like for instance, if you're looking at antimicrobial peptides, like the position, for instance, is important because it might help you to better understand the structure 3D or 2D. Now, in case I have two sequences that have the same reward, how do I choose which one, for instance, to prioritize or consider?
So in this case, when we had, let's say, this smiley face is like exactly the same smiley face, right?
Yes.
So like your question is that, I mean, in the basically the way we are doing this peptides would be in autoregressive fashion. So we won't have that problem anymore, right? Because there's like ordering, but because it's like a tree and there is like ordering, right? But like in this case, it's not a tree anymore. So this is like where the problem starts. So like the way we solved the peptide problem was in this fashion.
So are you saying it cannot happen that you have, for instance, two different sequences with the same reward score? Now, is it what you're saying? Because I'm assuming it could happen, right? So if it happens, and I know both sequences are different, but they have the same reward, for instance, if I want to select like new generated peptides to see which one maybe I'm sending to wet lab experiment, which one do I choose if I have two sequences or many which have the same reward?
I see. So the way we sample is that it's proportional to that reward. So they're going to be sampled similarly, the way I think about it. And then they're going to be sent to the wet lab. So I think that's the way, could be one way. Thank you. Is there anyone else?
Any other questions? Okay, then let's thank Fazide again.
Thank you.
Yeah, and with this, we're gonna finish today's day. Victor, do you want to say something?
So we're a bit early, so it's pretty unusual. So enjoy that. There's still some coffee left, and we'll see you tomorrow morning with opening words from Joshua, motivating GFlowNet, and we'll get into the core of why you're here. Thank you, everyone. Mathieu.
There's also leftover from the lunch. So if you are hungry or if you think you will be hungry later in the day, feel free to grab some food. Otherwise, we will let it to everyone at Mila. So help yourself.